Hello. Good morning, everyone. Okay. Firstly, let me check if I'm audible or not. Okay. Let me just check. Yes, so I am clearly visible, and am I audible to you all? Hi Kashina, sorry. Hi Kashinath. Hi Sagar. Hello everyone. Am I audible? Am I perfectly audible to you all? Good morning, Mir Zafar. Hi Hamsika. Hello everyone. Okay, yes. So I am perfectly audible and visible, I believe. So good morning everyone. I hope your morning is going really good. And if not, it's going to get better because we will be studying chemical kinetics and coordination compounds, right? They're one of the major topics, right? One of the most confusing also, because coordination, most of my students, they suffer a lot in coordination. So, but don't worry, I got you here. No worries, all your doubts will be cleared. Okay, hi Bharat. Okay, so let's start. Yeah, one request, when I'm solving the question, you solve the question with me, okay? Keep your pen and paper with you, okay, and solve the questions beside me, okay? There are numericals mostly, yes, because from these chapters numericals come, okay? Okay, so let's start, shall we? What are the chapters to solve? So the chapters are chemical kinetics and coordination compound. We will be solving these questions only from chemical kinetics and coordination compounds. It's written right there. Okay. Hi Amit. Oh, happy Ram Navami. Hi Pooja. Okay, so let's start. Okay. Let's start from chemical kinetics. And physics, I is strong in biology, I get good marks in KCET. So Jyoti, right, you need all of them. So even if you are bad in chemistry and physics, you still need to focus on that, like do those chapters which you are confident in, okay? You need all the marks now to score good, to get a good rank in KCET. Only biology won't suffice. 12th chapter. Yes, they are PU2 chapters. Yes, these are from PU2. Hi everyone. Hi Amulya. Hi Chetan. Hi Tilak. Hi Venkatesh. Okay, yeah, I'm starting. Yeah. You are more in a hurry than me. Okay. So, first question. The question says the rate of a gaseous reaction in this expression is this. Okay, so that means the rate law is given. KAB square. If the volume of the vessel is reduced to 1/2 of the volume, 1/2, okay, the reaction rate will be the reaction rate as original rate is. So how much times will it increase? Will it decrease? Will it become 1/8 times? Will it become 8 times? Will it become 16 times? Okay, let me ask quickly if we can add a poll. Let's see if we can add a poll here. Till then, you guys solve the question. Okay. No need of poll. Okay, no need of poll. So, C. Okay. So, some of you have solved the question. Just a minute. Okay, some of you have solved the question already, which is very good. Rate is equals to Ka. Okay, this is the rate law. Okay, now the question says that the volume of the vessel has been reduced to 1/2. Has been reduced to 1/2. This is what? Concentration. How is concentration and volume related? So we know that our concentration is equals to number of moles of A by volume, right? Similarly for B also, it will be number of moles of B by volume. Clear? This much we know. So that means your rate, I'll call it R, will be equal to Na by V, K times Na by V times Nb by V square. Clear? That's how your concentration is related to volume. Concentration is equals to number of moles divided by volume, right? Molarity you know, right? Number of moles of solute present in 1 liter of solvent, 1 liter of solution. Okay, so here if we solve this equation, we will get K Na Nb square by Vq. This is the original rate law. This is the original rate law, right? Now, if we reduce the volume to 1/2, that means now the new volume, V new I'll write here. The new volume is V by 2, right? Now what will we do? We will substitute this in this rate law. This is the rate law for this reaction. This is the rate law for this reaction. We'll substitute this value in this one. How? So now your rate, let me call this new rate. So I'll call it Rn. I'll call it Rn, new rate, which will be equal to K, concentration of A. It is Na by V, but now the new volume is V by 2. So that means it will become Na by V times 2. Right? Simple? I hope it is clear. Yes. AB. Okay. And the volume of B. Similarly, if we substitute for B, the value will look like this. V by 2 we substitute here and it is square, right? So Nb square upon V square times 4. That will be your final value. If we solve this expression, what do we get? We get 8 times K times Na Nb square upon Vq. Isn't this expression similar to this original rate? Right? K Na Nb square by Vq, K Na Nb square by Vq. So I can write here 8 times the R, which is the original rate. So that means the new reaction rate will be 8 times the original reaction rate. Okay? The new reaction rate will be 8 times the original reaction rate. Okay? I hope it is clear. So that means the answer is option C. And I see most of you answered C only. Yes, C only you answered. Next question. In which one of the following reaction rate constant has the unit mole liter inverse second inverse? In which of the following reaction the rate constant has the unit mole liter inverse second inverse? Firstly, you should know which order reaction is this. So the unit of rate constant is mole liter inverse second inverse. What is the answer? Some are saying A, some are saying, Tanishka is saying A, Preetham is saying D. Okay, let's see. First of all, which order of reaction? This is 0 order, right? This is 0 order. A short trick you all know, I think. To calculate, to determine the unit of rate constant, this formula we use, mole raised to power 1 by n, liter raised to power n minus 1, second inverse. N is the order of the reaction. Here n is the order of reaction. Okay. Now if we substitute for 0 here, n equals to 0, the expression will be mole liter inverse second inverse. Okay. This is also the unit of rate. Rate unit is also mole liter inverse second inverse. It doesn't change, it remains constant like that only. Okay, 0 order. Yes, correct, Nikhil. So this reaction is 0 order. According to the unit of rate constant, this reaction is 0 order. Now let's see one by one. Acid catalyzed hydrolysis of ester. If we do acid catalyzed hydrolysis of ester, what is that reaction? Acid catalyzed hydrolysis. That means the water is in excess, right? It is an example of pseudo first order reaction. It is an example of pseudo first order reaction. Right? So that means it isn't a 0 order reaction. What are we looking for? We are looking for a 0 order reaction. Okay. Now for second one, it looks like this, right? chloroform, you have chlorine gas, it reacts with chlorine gas, it forms carbon tetrachloride. But this reaction it has a fractional order. It has a fractional order of around 1.5. The order is 1.5. It's not zero order reaction exactly. Okay. Similarly, this reaction also, the nitrogen oxide reaction, this reaction is a third order reaction. The order is 3. For this reaction, the order is 3. For this reaction, the order is fractional 1.5. So this reaction, our only source is this reaction. What happens here? You have a gold surface. On this surface, HI molecules. These all are the HI molecules. The gold surface becomes saturated with all these HI molecules, right? After one point, it becomes independent of concentration. That's zeroth order reaction, right? Independent of concentration. Where your rate is independent of concentration, that is your zero order. This reaction is your zero order reaction. Decomposition of HI on the surface of gold. So how many of you answered D? Yes. Zero order C. Pooja, it's not C, it's D. C. This reaction is third order reaction. Okay? Yes, the answer is D. Next question. For this reaction, rate is given and rate constant is also given. Okay, rate is given and rate constant is also given. You need to find the molar concentration of PCl5 at that instant. You need to find the concentration of PCl5 at that instant. Okay, what should be the answer? You calculate it. Okay, till then I'll explain. So we are given what? What are we given? We are given rate, which is 1.02 times 10 raised to power minus 4 mole liter inverse second inverse. And we are also given rate constant, which is K, which is equals to 3.4 times 10 raised to power minus 5 second inverse. One thing is clear, we are not given anything about the order of the reaction, but we know from the unit of rate constant that the order is first order. The reaction is first order. Okay. Now, how do you write rate law for first order reaction? Simple. Rate will be equal to, this is a proportionality constant here, rate constant times the concentration of reactant raised to power 1. Why? Because the order is 1. Because the order of the reaction is 1. Okay. Now here what do we know? Rate is known to us. K is also known to us, right? We need to find PCl5 concentration. What do we need to find? We need to find PCl5 concentration. So many of you are answering D. Some of you are answering B. Hi Mohi. Okay, so let's calculate it. It's just simple calculation. Just one thing was there. We need to find the order because it's not written clearly. What do we have here is second inverse. We know second inverse is the unit of rate constant of first order reaction. That means the rate law will be written like this. This is rate law, right? Rate of any reaction is directly proportional to the concentration of the reactants. Concentration of the reactants raised to power of their molar concentration, raised to the power of stoichiometric coefficient, or raised to the power of order, you can say, right? This thing is determined experimentally. This thing is determined experimentally, not theoretically. Okay? Okay, so many C's also there. Okay, let me just solve it first. 1.02 times 10 raised to power minus 4 will be equal to 3.4 times 10 raised to power minus 5. And this we need to find. The PCl5 concentration we need. Okay, so that means PCl5 will be equal to, if we divide them, here you can apply a little bit of approximation. So the answer will be 10 by 3 something. Let's say I just round it off. I say it's like around maybe 10 by 3. So it will be around 3.33, right? Which is the closest one here? B. The closest one. 3 is the closest to this value, right? Here you can apply a little bit of approximation. Yes. So how many of you answered B? Let me see. Preetam answered B. Tanishka, Preetam. Okay. Then you have Ajma, Ved, Wasim. Okay. Chetan, it's not C, it's B. Darshan also, calculation error. Okay. Good morning. Good morning, Ab Patila. What's your name? Ab. Okay. B done. Okay, so every one of you answering. Thank you. You all are answering correctly actually. The calculation was really easy. It was a straightforward question. Okay, next question. Let's move on to the next one. A first order reaction is half completed in 45 minutes. How long it need 99.9% of reaction to be completed? Tell your name, Mohi. Hi, Mohi. Okay, so you're answering for this question already. Venkan, okay, it's not C. Okay, let me calculate it first. Okay, first order reaction is half completed in 45 minutes. That means T half is 45 minutes. Always remember, when you're reading the question, check the unit. The unit is in minutes, but the answer is in hours. So somewhere you need the conversion. Okay, but we are not doing it right now because it will make the calculation a little bit intense. So we are simplifying it first. Okay, T half is given 45 minutes. How long does it need 99% of the reaction to be completed? 99.9% is completed. Okay, so we know how to determine the rate constant for first order reaction. What is that formula? I believe it is like this. This is the expression, right? 1 by T, 2.303 by anything. K you want to know, you send the T here. Okay, one more thing, you might get confused. Sometimes even I don't remember all the formulas. So I remember one formula. For first order, the equation is like this. K1 is the rate constant of first order reaction. So what I did here, I took logarithm. Okay, ln A will be equal to ln of A naught minus K1 of T. So if I just take it on the left hand side, clear? This is the expression will become, right? And what I need to convert this natural logarithm into log to the base 10. So what I'll do, I'll multiply it by 2.303 and it will convert into log. That's like a simple way of remembering the formulas when you don't know. Just remember one base formula and then from there you can determine however the quantity that is given, the data that is given, accordingly you modify that. Okay. Now this expression, yes, that is the expression we get. What is given here? T half is given. Okay, one more thing that is given here, I know that. This is the expression that we'll use to calculate the final time. But T half is given and we know T half is equals to what? 0.693 by K. 0.693 by K for a first order reaction. The reaction is first order. So if you calculate it, it will come out to be K will be equal to 0.693 by 45. What I need to do, I need to calculate the time when the concentration, but 99% of the reaction is consumed. So how much reactant is left? If 99, let's say we are taking 100% and in that 99.9% is consumed, how much is left? 0.1. 0.1% is left, right? So what is this? This is your A. It is the left concentration, the remaining concentration of reactant. A naught, initial concentration is what? Initial concentration you can take 100, no worries. Initial concentration is 100 and when 99% of reaction, 99.9% of reaction is completed, the amount of reactant left is 0.1. One more thing, whenever you're doing questions regarding half-life, 75% life, any life, okay, we are talking about the left amount of reactant. We are not talking about the amount that is consumed already. We are talking about the amount that is left because only that amount will further react and will give us the product. So that is of importance, not the amount that has reacted already. T half, half is reacted, the half unreacted portion is of our concern. Similarly, 99.9 has reacted, so that means this is our value that we need. Only this much reactant can react further on. Okay, so we have almost all the values. K is this. Okay, so we'll substitute it and find the time, which will be 2.303 by K. K is 0.693 times 45 log of A naught is 100 by 0.1. Okay, if I calculate it, what will be the answer? that in our college we take R instead of A. Yeah, that works. Whatever reactant you are using. I normally use this kind of reaction, IAP. That's how I learned it. But you can use reactant to product also. R is fine as long as you know R0 and R. Okay, what is R0 and what is R? D, A, B, C, D. No, that's not correct. Okay, so if you calculate this simple equation, right, 2.303 by 0.698, the answer will come out to be 450. Now remember, we haven't converted it, so that means this answer is in minute, 450 minute. Okay, now if you convert this 450 into hours, this minute into hours, so you'll divide by 60. Answer is 7.5 hours. 7.5 hours. How many of you answered D? Let me see. D, yes. So yes, Pooja answered D, we answered D. Okay, good morning Mithun. Is it clear? Any doubt? What about log value? Yeah, that's actually a really nice question. Okay, I'll give you. Just remember up to log 5. That's the max you'll need. If any value is beyond that, normally they provide all the log values in the question itself, but if it's beyond that, you will be given in the solution, in the question only. Remember log 1, what is the value of log 1? Okay, I'll just do here. Log 1 value is 0. Log 2 value is 0.301. Log 3 value is 0.477. Log 4 value is 0.60. Log 5 is 0.699. It's something like this. Okay. These are all the values that you need. You don't need anything beyond that. If you just remember them, that will be much easier when you're doing the calculations. Okay. No, log 10 is always 0. Log 10 is always 1, not 0. Good morning everyone. B answer. Oh, you already solved it. Nice. Okay. See, this is the log values you need. You just write it down somewhere, revise it. It's very easy. Log 1 0, log 2 0.301, 3 0.47, 4 0.60, 5 0.69. Okay. Okay, I'll just erase it. Now, the question is half-life of a first order reaction is 20 seconds. Half-life is 20 seconds, okay, and you are given 80 seconds and the initial concentration. You need to tell after 80 seconds how much concentration is left. How much concentration is left after 80 seconds. Okay, so there are two methods to do that. If you know the formula, it's straight formula based question. If you don't know the formula, there is a slight longer version also. We'll solve using both of them. Okay, so if firstly let's solve the longer one, then we'll do the formula one. Okay, so firstly the thing is given that T half is 20 seconds. The T half of this reaction, half life is 20 seconds. If half-life of this first order reaction is 20 seconds and the initial concentration is 0.2 m. After 80 seconds, how much concentration is left? So I know that if I start now, after 20 seconds, a bell will ring and half of the concentration has reacted. Half of this concentration would have reacted. Okay, 20 seconds. Then in the next 20 seconds, whatever the amount is left, let's say 0.1 is left, in the next 20 seconds, what will happen? This amount will also get halved. This amount will also get halved, right? And in the next 20 seconds also. So how many half-lives are possible in this 80-second timeline? How many half-lives? You have 80 seconds, right? And one half-life is of 20 seconds. So that means how many half-lives we have? 4 half-lives we have. That means the reactant concentration will be halved 4 times. It's not a straightforward calculation. You can't just divide it by 4 and get the answer. The thing, you have in maths you have interest, and then you have simple interest and you have compound interest. So it's like a compound interest here. Okay. So what is happening here actually? after 80 seconds, how many half-lives are there? 4 half-lives has been done. Okay, 4 half-lives has passed. So what will be the concentration? Okay, first half-life, the concentration is 0.2. After 20 seconds, the concentration is halved, 0.2 by 2. That means now the concentration is 0.1. Clear? In second half-life, now after this second half-life come, right? The concentration of reactant is 0.1. After this 20 seconds, after the next 20 seconds, what will happen? This concentration will also get halved. Half of it has reacted, only half is left, which is 0.05. Clear? In third half-life, we are having how many half-lives? 4 half-lives, right? We are having 4 half-lives. Okay. So in third one, we have the concentration 0.05, right? Now what will happen in third half-life? It also will get halved. So 0.05 by 2, which is 0.025. Now this is the concentration of reactant left after third half-life. This is the concentration of reactant left after third half-life. Okay. Now we have one more half-life left, fourth half-life. There are 4 half-life, right? So this concentration will also get halved. Half of it has reacted, only half will be left. So that will be 0.025 by 2, which is 0.0125. This is the concentration that will be left after these 4 half-lives. Firstly, you should understand the concept of half-life. So it's like if I took this big of something, let's say if I took this big of any object, okay, after half-life, after one half-life, this half part has reacted, only this part is left, okay, this is left. Now in the second half-life, what will happen? This will be the reactant, the left amount will be the reactant, right? And half of that will get reacted. Clear? So this much is left. Similarly, in third half-life, what will happen? This also get halved. Let's say this much is gone, we'll get this much, right? And so on. The half-lives work like that. Whatever amount of reactant you have at that point, it will get halved. Half of that will get reacted. Okay. So this is the long method. The short trick method, or you can say the formula based, how many half-lives are there? You can calculate 4 half-lives are there, and concentration at any half-life you have, like concentration and the reactant concentration and the concentration at any instant. Okay, I'll just write the formula first. The concentration at any instant is equals to the concentration of the initial concentration of the reactant divided by 2 raised to power n. Here n is the number of half-lives. How many half-lives are there? Okay, now the initial concentration was how much? 0.2. 0.2 by 2 raised to power n. N is the number of half-lives. How many half-lives we had? 4. How many half-lives we have? 4, right? 0.2 by 16. So if I calculate it correctly, it will be 0.0125 m only. Okay, so that means your answer is option 2, B. Okay. There is no H in my name actually. My name is Ekta only, EKTA. Ekta ma'am. Okay, if you have any doubt. How many of you answered B? Yes. BB answered B. Tanishka also answered B. Good morning. Okay. Done? Clear? So there is a long method. If you don't remember the formula, just half the concentration, half whatever concentration is left. Calculate the number of half-lives, half the concentration. But sometimes there will be too much, too many half-lives. If it is like 8 half-lives, then how would you have done it? Then you remember this formula, A0 by 2 raised to power n. The concentration of the reactant that is left will be equal to A0 initial concentration divided by 2 raised to power n. N is the number of half-lives. Okay, clear. Okay, get 92 plus in chemistry board exam. So should I give second exam or just focus on KCET? If you are getting 92 plus in your chemistry exam, yes, you should focus on KCET, I think. Yeah, That's actually really good. You understand chemistry really nice, I think. Yeah. Okay. Questions we are solving, we'll know how many questions are there with time. Again, explain the formula method. So it's very simple. So this formula method, this is the direct formula. This is the amount of reactant, concentration or amount of reactant that is left after n number of half-lives. Okay, this formula will be used when you know the number of half-lives are there. Okay, so we know the half-life is 20 seconds, one half-life is 20 seconds, and we are given the time. So we can calculate if one half-life is 20 seconds and we are given 80 seconds, that means there are 4 half-life possibles. There are 4 half-lives possible, right? Only then you'll use this formula. Then the concentration of reactant that is left after n half-lives is equals to A naught, which is the initial concentration, divided by initial concentration of reactant divided by 2 raised to power n. N is the number of half-lives that is possible in that time limit. For example, in 80 seconds, 4 half-lives were possible. Why? Because 20 seconds is 1 half-life. Okay? I hope it is clear. This is the very easiest one. You just remember it. This is the amount of reactant that is left after n half-lives, which is equals to the initial concentration A naught, initial concentration of reactant A naught divided by 2 raised to power n. N is the number of half-lives. N is the number of half-lives. I hope it is clear, Mahadev. So example in here, 4 half-lives were there, 2 raised to power 4, and the initial concentration was 0.2. So that's how we calculated it. It was a simpler method. Okay. It's just a simple formula, but use it only when you know the half-life and the number of half-lives possible in that time span. Okay. If somehow time was not given, you would not be using this method. Okay. B. Did you eat? Yes, I had breakfast. Did you guys have breakfast? Next question. The rate constant for 2 different reactions are this and this. We have to find the temperature at which K1 equals to K2. So, K1 should be equals to K2. This is the condition. Straightforward, right? The rate constants are also given. K1 is equals to 10 raised to power 16 times e raised to power minus 2000 by t. Okay. We need to find this temperature. Okay, we need to find this temperature. Don't substitute T1, T2 here. Why? Because we need to find the single temperature at which K1 equals to K2. No other variable quantity is there, right? Only T is there. So T should be same. Okay. Yes, Lakshman, what was your question? It's in the description of this live also. I am Ekta ma'am. Okay, my name is Ekta. Nice to meet you all. Okay, I'm your Ekta ma'am. Okay. Option B. Okay, no, it's not option B. Let's calculate it first. So we need the value of temperature. This data is already given to us. We need the value of temperature at which K1 equals to K2. This is K1 and this is K2. Both of them should be equal. So now if I calculate it, 10, I take that side. Okay, it's a simple calculation. If I take that side, it will become 10 raised to power 16 by 10 raised to power 15 e raised to power minus 2000 by t. Let me take this on the right hand side also. Okay, if I take it on the right hand side, it will become e raised to power minus 1000 by t upon e raised to power minus 2000 by t. Now, simple calculation, this will become what? 10, 16 minus 15, it will become 10 equals to, and this will become what? E raised to power minus 1000 by t plus 2000 by t. So that means I can just write here 1000 by t, e raised to power 1000 by t. 10 is equals to e raised to power 1000 by t. Okay, now what is the anti-log of this? Not anti-log, log of this. Okay, this is exponential. For exponential, the logarithm is natural logarithm. Okay, we take natural logarithm both sides. ln of 10 equals to 1000 by t. Now one thing here, natural logarithm, which is ln, and log to the base 10, log to the base 10, okay, that they are not same. They are not same. You know that already. They are not same, right? You can't just say ln 10 is not equal to 1. Log of 10 is equals to 1. Log to the base 10. Log of 10 is equals to actually 1. 1, but ln of 10 is not equal to 1. What is it is equal to? We'll convert it into log to the base 10. How? ln of 10, we'll write 2.303 log of 10. Yes, 2.303, this is 3 log of 10 is equals to 1000 by t. Clear? So that means t will be equal to what? 1000 upon 2.303. T is what? 1000 upon 2.303. 1000 upon 2.303. How many of you answered C? This is the temperature. This is the temperature. This mistake you might have done it, right? It is to confuse you. ln of 10, because ln of 10 is not equal to 1. You can't just put 1 and then the answer will be 1000. This, see, if you put ln of 10 1, the answer will be 1000, and this option is given 1000 to confuse you, right? So you should use your brain here that ln of 10 is not equal to 1. ln of 10 is equals to 2.3 something, okay? But we know that to convert natural logarithm into log to the base 10, we multiply by 2.303. So that's how we did it. 2.303 log of 10, and that means your temperature is 1000 upon 2.303. Yes, the answer is C. Correct. I hope you solved it along me. Okay, along with me actually. Okay, next question. This is the reaction. Is the diagram visible to you all? Good morning, everyone. So is the diagram visible to you all? If not, I'll just draw it. Okay. So I'll just explain what is happening here. This is the reaction curve. I hope it is visible. It's not visible, right? I think after this it will be visible. Okay. This side we have reaction coordinate, and on this side we have energy. In this case, potential energy. Clear? Is it visible now if I'm drawing it with red ink? Is it visible? Okay. This energy is given, which is the activation energy, which is 215 kilojoule. 215 kilojoule. Okay, now this is the change in enthalpy, 90 kilojoule. These are the product, these are the reactant. Okay, few things are here. Okay, few things which are not related much here. Okay, not to the question at least. You know, ma'am, draw by side on the black area. Okay, I'll try. I'll draw it here only. Correct. 1 second. I'll draw it here. Okay, we have reactant, we have product. Here it is reactant, here it is product. Okay, then we have this. This is the activation energy. Here we have potential energy on the y-axis, reaction coordinate on the x-axis. But this activation energy, this is here. This is the activation energy, 215 kilojoule, and this difference in energy, the change in enthalpy between the reactant and product, delta H. This is equals to 90 kilojoule. Simple. Okay. We need to find the activation energy for the reverse reaction. We need to find the activation energy for the reverse reaction. Okay? Okay, good, correct. Thank you, it's visible for you all. Sorry, I didn't see that. I thought it will be visible. Okay, see, what is here? Firstly, you should understand few things. Is it exothermic or endothermic? Is the reaction exothermic or endothermic? You see, you know exothermic and endothermic only by one thing, by this relation, reactant and product position. Okay, if reactant is lower in energy and the product is higher in energy, if the reactant is lower in energy and the product is higher in energy, that means this product, answer is 125 kilojoule. Yes, correct, Nalin. Three. No, 3 is not the correct answer. Now I am not visible. Oh, because I was reading your guys' comments. You guys are answering correctly. Okay, now see. For this reaction, we know this is an example of endothermic reaction. Why? Because there is a difference in energy between the reactant and product. Reactant has lesser energy than product. That means this product absorbed some energy, and if absorption of energy is there, what is that? That is endothermic reaction. That is endothermic reaction. Okay, that is your endothermic reaction. Now one more thing. Okay, so that means this is the activation energy. This is the peak. From reactant to product, from the reactant, you need to give this much energy. The reactant should have this much energy. How much? EA. This 215 kilojoule energy to convert into product. If it has energy equal to or greater than the activation energy, only then the product formation will happen, right? That's the activation energy concept. What do we know about activation energy? That the reactant should have equal to or greater than the energy. The reactant should have equal to or greater than the activation energy, this much energy, only then the product formation will happen. Okay, that's what we know. Now, if you want to talk about the reverse reaction, which is from product to reactant, right? From product to reactant. Now, in this case, what will happen? This will become our reactant. The product will become our reactant. And then how much energy does product need? To convert it into reactant, this much. It need to reach to this peak, but it is already here. The product is already here. Okay, the product is already here. The product need to reach to this peak. Clear? This is the activation energy for product. This is the activation energy for reactant. Clear? This is the activation energy for product, and this is the activation energy for reactant. This value is given. This change in enthalpy, the difference in enthalpy between energy between reactant and product, it is also given, which is 90 kilojoule. 90 kilojoule. Okay, this value is given, this is given. So how do you calculate it? From this it is simple. How? This whole value minus this, that means this whole value, right? This complete value. If I subtract this value, I will get this value, right? Clear? I hope that is clear. So that means the answer will be 215 minus 90 kilojoule. That is the activation energy required for backward reaction. That is the activation energy required for backward reaction, which will come out to be 125 kilojoule. 125 kilojoule, which is D. Correct. Formula, yes, we do use a formula also, but that's how you understand conceptually. Okay, so sometimes you may not remember all the formulas. So if you know how to apply the concepts, you know that from reactant to this point is the activation energy required by the reactants. From product to this point is the activation energy required by the product to convert it into reactant if the reaction is going in backward direction. Okay, so if you know all these concepts, you can calculate it. Now one formula is also there, correct? The formula is this: the change in enthalpy between the reactant and product is equals to the activation energy of forward direction minus the activation energy of backward direction. That is the formula. In that case, whatever be the sign of your delta H, because enthalpy can be positive, enthalpy can be negative, depends on exothermic or endothermic reaction, right? Increase the volume little bit. Okay, let me see if I can increase it little bit. I am adult, you know that, right? Yes. Okay, ma'am, what's your age? Wow. What's your name? Your Isa, ma'am, correct. Guys, focus. You have to solve all these questions on your own in the exam. I won't be there to help you all, okay? So the formula is simple. Delta H equals to EF minus EB, which is change in enthalpy, or difference in energy between the reactant and product, equals to the activation energy of forward reaction minus the activation energy of backward reaction. Clear? If I just substitute all the values here, I'll get the answer. 90 equals, for forward it is 215 minus backward. This I need to find out. EB will be equal to 215 minus 90. 215 minus 90, which again will be equal to 125. So use either this method or use either that formula 1 method. Okay. Okay. Next question. For this reaction, okay, this value is a little bit tricky written here. 10 raised to power 5. This is 10 raised to power 5. Okay, I'll just write clearly here. This is the value of rate constant. At temperature 300 Kelvin. The value of A. What is A? A is this collision factor, right? Collision frequency factor. You know that equation, this one, Arrhenius equation, right? K, rate constant, equals to A, which is the collision frequency times E raised to power minus EA by RT. EA is the activation energy, R gas constant, T is the temperature. Clear? Okay, now we need to find the value of A at infinite high temperature. Infinite high, that means I can say temperature is around infinity. Okay, now let's see. This is the expression for, this is the Arrhenius equation, right? This is the Arrhenius equation. I think everybody knows that. And if you want to write the log form, just simply write it as it is. ln of K will be equals to ln of A minus EA by RT. And if I want to convert it also, then I can write it log of K equals to log of A minus EA by 2.303 R. No, actually, the one for where two rate constants are given, the equation is this. Log of K2 by K1 will be equal to EA by 2.303 R 1 by T. If K2 is up, you write 1. 2 is up, you write 1 minus T2. And if you don't remember this K2, K1, just one more thing you can do. T1 and T2 is written here, right? So that means T2 minus T1. The expression will become T2 minus T1. And T2 is always greater. T2 is normally higher temperature. So that means this will always come positive, right? So remember, T2 should always be greater. That's why it's written like that, little bit, okay? Or you can write, remember like this, K2 by K1, 2 by 1, so 1, 2, okay? Now, see, here we don't need these expressions, these are just for your revision. We need this only, okay? What are we given? We are given that temperature is infinitely high. That means temperature is close to infinity. Now tell me one thing. Here if I see, okay, it is minus EA by RT. Now temperature is infinity. Infinitely high temperature. What do I know? 1 by infinity. What is 1 by infinity? 0. What is 1 by infinity? 0, right? 1 by infinity is 0. That means this whole thing will be 0. And if I substitute the 0 here, what will I get? K will be equal to A e raised to power 0, and any number, anything raised to power 0 is 1. Anything that is raised to power 0 is always 1. So that means A will be equal to K. The collision frequency factor is collision factor. It is always equal to K in this case. And what is the value of K? What is the value of K? 6 times 10 raised to power 5. 6 times 10 raised to power 5. The answer is option D. Thank you, Pavni. Once again, not understood. Okay, I'll explain once again. Okay, now see. So we are given the value of rate constant at 300 Kelvin. This is the value of rate constant at 300 Kelvin. Okay. You need to find the value of A at an infinitely high temperature. Now we know, according to Arrhenius equation, this is the equation, K equals to A e raised to power minus EA by RT. This is the Arrhenius equation, simple equation, right? Now in this Arrhenius equation, A is there, right? We need to find the A, that's why we're using this equation. We know the thing is, the temperature is infinitely high. Infinitely high, that means you can consider it's infinite also. The temperature is infinite. So I just wrote this expression, minus EA by RT. Here temperature is there. If temperature is infinite, in denominator if infinite is there, anything by infinite is 0. Anything by infinite is 0. So that means this whole factor minus EA by RT will become 0. Minus EA by RT will become 0. Now if this is 0, e raised to power 0 is what? 1. E raised to power 0 will be 1. That means your this Arrhenius factor, this A, which is your collision frequency, let's call it A only, don't complicate it. This A will be equal to rate constant K. This A will be equal to rate constant K. And what is the rate constant? It is 6 times 10 raised to power 5. Rate constant is 6 times 10 raised to power 5. Okay. Okay, who asked it again? Chidambar, is it clear? The simple equation we used, just one thing is written, infinitely high temperature. If temperature is infinite high, that means this factor becomes 0. And if this is 0, that means E becomes 1. E raised to power 0 will become 1. And your A will be equals to K. Okay. Right? These are for your revision actually. I was trying to tell you if you didn't remember them. The way of writing I told you. This is not related to this question. Next question. For this reaction, yeah, this one was the one we did back then, right? We solved a graph, right? This is similar to that. Here the value is given, EA is given, delta H is given. One more thing is there, when a catalyst is added, the activation energy decreases by 10 kilojoule per mole. So now the new activation energy is what? 50 minus 10, which is 40 kilojoule per mole. Okay, and delta H is what? Minus 20 kilojoule per mole. What do we need to find? Again, we need to find the activation energy. EA is the activation energy for the backward reaction. Okay, activation energy for the backward reaction in presence of catalyst. The thing is, it is in presence of catalyst. If catalyst was not there, you will use 50 only. You will use this 50 only. But if catalyst is there, you will use the activation energy in case of catalyst. What does catalyst do? They lower down the activation energy, right? Actually, it's like this. Let's say if you are here and you have to go here. Okay, and by someone make a road like that, like this, 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 and this. Okay, this is one pathway, one path to reach from point A to point B. Now, some other person came, let's say that person name is Catalyst. Catalyst came, and what Catalyst did? It made a new road from A to B. From A to B. They made this new road, A to B, right? What happened here? Still, product formation is happening. Reactant is getting converted to product, right? But a different path is given, a different path with lesser activation energy is provided. A different path with lesser activation energy is provided. That is the role of catalyst. This is with the catalyst and this is without catalyst. This is without catalyst, okay? The reaction takes much longer time. If you add a catalyst, it generally, positive catalyst, it generally lowers down the activation energy. How much? It lowered down by 10 kilojoule in this case. In this case, it lowered down the activation energy by 10 kilojoule. So your now new activation energy is 40 kilojoule per mole. Okay? Yes. Okay. For question 8, A, D option, yes, D is the correct answer. Correct. So, we need to find the backward activation energy for backward reaction. Okay, we know the formula, right? What was the formula? Even if you don't know the formula, use the formula first. Delta H is equals to E forward reaction minus activation energy of backward reaction. Again, we need to find the backward one. This is given minus 20 equals to, forward one is 40 kilojoule minus EB. That means your activation energy for backward reaction is 60 kilojoule. 60 kilojoule per mole. Okay, so what is the answer? The answer is option yes. Okay. Option D. Some of you are answering option D also. Option A. Yes, option A is the correct answer. 60 kilojoule per mole. Okay. Let's move on to the next question. Which is the wrong statement? Wrong statement. We are asking for wrong statement. Divya, do you have any train to catch? Teach fast. Once again. You want me to solve the last question once again or something? Okay. Answer this question. Which of the following is a wrong statement? So first one is rate constant K equals to the Arrhenius constant A if EA equals to 0. Firstly, you should know that expression K equals to A e raised to power minus EA by RT. This is the Arrhenius equation. Okay, here EA is 0. If EA is 0, if this is the case, EA is 0. That means K will be equal to A e raised to power 0. This is 0, whole thing becomes 0. Then again K will be equal to A. We just solved it, right? That means in that case, if activation energy is 0, the rate constant become equals to the Arrhenius constant. If activation energy is 0, then rate constant become equal to the Arrhenius constant, right? So that means this is a correct statement, not incorrect. We are looking for the incorrect one. Next, e raised to power minus A by RT gives the fraction of reactant molecules that are activated at the given temperature. So yes, one scientist was there, Maxwell Boltzmann, two scientists actually, they said that this is the fraction of molecules that have activation energy, that have kinetic energy actually equal to or greater than the activation energy. These are the fraction of molecules. Let's say if I have 100 molecules, in those 100 molecules, 50 molecules have energy equal to or greater than the activation energy. Greater than the activation energy, right? At any given temperature, okay? That fraction is represented by this, okay? Now those 50 molecules will undergo reaction, right? They will convert from reactant to product, okay? So that is also correct. That is also a correct statement. ln k versus 1 by t plot is a straight line. ln k versus 1 by t plot. So let's just, I don't know the ln relation. Let's say I don't know the ln relation. So what I'll write, ln of k from this equation will be equal to ln of A okay, ln of k will be equal to ln of A minus EA by RT. Y equals to mx plus c. If this is y axis, okay, this is c, mx. x is what? 1 by t. 1 by t is x, ln of k is y, because the graph is being plotted between ln of k versus 1 by t. So the slope is minus EA by r, and slope is minus EA by r, and the intercept is ln of a. This is the equation of a straight line. Y equals to mx plus c is the equation of a straight line. So that means, yes, if you plot ln of k versus 1 by t, if you plot ln of k versus 1 by t, the graph will come out like this. Minus EA by r will be the slope. This intercept value is ln of a, right? This will be your final graph. So yes, this is a straight line. This is a straight line. Yes, the wrong statement is the last option. Yes, last presence of catalyst will not alter the value of EA. Yes, it does alter. Why? How? It actually decreases the value of activation energy. It actually decreases the value of activation energy. Okay, so that means the incorrect statement is your last option, because presence of catalyst does alter the value of EA. How? I just told you, it alternates, it provides an alternate pathway. It provides an alternate pathway for the reaction to happen. Okay, so that means it lowers down the activation energy. The amount, see here, how much fuel would you have used, right? If you went like this. But if you went from this path, only small one, I don't know exactly, but like 1 liter will be more than enough for you. Okay, that is the role of catalyst. Yes, so the correct answer is option yes. Oh, that's nice actually. 9 once again. First order and zero order graph. Hold on a second. Let me explain this first actually, then I'll draw the graphs. Okay. For the reaction, this reaction EA equals to activation energy is given. The enthalpy change is also given. Okay. When a catalyst is added, it decreases the activation energy by 10 kilojoule per mole. If it decreases by 10 kilojoule per mole, that means the new activation energy is 40 kilojoule per mole, right? 50 was there, it decreased by 10, that means the new activation energy is 40 kilojoule per mole. Now we need to find the activation energy of the backward reaction in presence of catalyst. We need to find the activation energy of backward reaction in presence of catalyst. So if catalyst is there, this is the activation energy for forward reaction. This is the change in enthalpy. It remains same, it didn't change. Yes, it remains same. Okay, because that barrier is different, the energy gap is different. Okay, if you go see like this, okay, this is different and these all same. What does catalyst do? Catalyst will make it follow this line like this. Yes, this is in presence of catalyst and this is in absence. Clear? So it just lowers down that barrier. Okay, this value is given to us as minus 20. So if it is minus 20, actually the reaction graph is like this actually. Let me draw it. Okay, it is like this. This is minus 20, this is 40, right? Yeah, this is 40. So in this case how much energy? This is the reactant and this is the product. In this case, how much energy is needed by the product to reach the activation energy? This is up till here. So we'll add these 40 plus 2. If you do it graphically, what are we doing? We are going from here to here. This is 40, this is minus 20. So if you add this whole will come 40 plus 20. That is your 60. That is 60 kilojoule. Okay, and if you don't know how to use this, you have this straight formula: change in enthalpy is equals to the activation energy of forward reaction minus activation energy of backward reaction. For forward reaction it was 40. Why? Because of the catalyst. For backward reaction we need to calculate delta H, change in enthalpy is minus 20 kilojoule. So you add minus 20 and then your backward reaction, the activation energy for backward reaction is equals to 60 kilojoule per mole. 60 kilojoule per mole. Okay, can you explain? Mir, I hope your doubt is clear. Okay, hold on a second. Okay, this expression okay. What is the equation for zero order of a reaction? Zero order reaction, the equation is simple. A equals to A naught minus KO T. KO means the rate constant of zero order reaction. This looks like a straight line graph, right? If I plot y on one side and I take t as the x, y as the a, this will be mx plus c. So if you plot a on the y-axis and t on the x-axis, the graph will have a intercept of a naught, and the slope is negative, minus k naught. Right? This is, and this intercept is a naught. That is the graph. Okay? This intercept value, this point is your a naught. Okay? And this slope of this graph is minus k naught. It is a straight line. That is for your zero order reaction. Okay. Now for first order, actually two graphs are possible if you want to draw. We have two expressions for first order. A equals to a naught e raised to power minus k1t, rate constant of first order reaction. So if I plot here a versus t, if I plot here a for this expression a versus t, it will be an exponential plot. It will be an exponential plot because obviously exponent is there. So the exponential plot will look like this. It will look like this. But what I do, if I convert it, if I take a logarithm both side, ln of a equals to ln of a naught minus k1t. Now if I plot ln of a versus t, now this expression is y equals to mx plus c again. That means the slope is minus k1 and the intercept is ln of e naught. Okay, slope is minus k1 and the intercept is ln of e naught. This is the value of the intercept. Okay, so depending on the type of equation, you can make the graph yourself also. Mostly a straight line, but for zero order the graph is a versus t. For first order the graph is ln of a versus t. For first order the graph is ln of a versus t. Okay. Okay, clear. Yeah, okay, sure, I'll try. 34.7. Yes. Yes, that's correct. Answer is 34.7. Okay, I'll be back in 2 minutes. Okay, just give me 2 minutes, I'll be back. So let's start. We have coordination also, you know. I'll see how fastly you'll answer in coordination. This one you can answer, I know. The questions are a little straightforward. They are coming formula based only. Okay. You cannot see me. Okay, let's start. What is the activation energy if the reaction rate is doubled when the temperature is raised from 20 degrees Celsius to 35 degrees Celsius? Again, very simple. I hope you have written this down. I'm going to erase it because I need this space to solve the question. Very simple, very easy question. You all need to know only the Arrhenius equation. What do you need to know? The Arrhenius equation, and from there you will be able to solve it. But here two rate constants are given. Here two rate constants we are talking about. Rate is doubled. Okay, so if I have K1 and a K2, so let's say K1, if K1 is K, then at 35 degrees Celsius. Okay, this is at 20 degrees Celsius, and this is 2K, which is at 35 degrees Celsius. This is the data that is given. Okay, rate is doubled, the temperature is raised from 20 degrees Celsius to 30. Now 20 means 20 plus 273, 293 Kelvin, and 35 means 35 plus 273, 308 Kelvin. Clear? We need to convert the data in Kelvin only because these values are given in Kelvin only. Okay. Okay. Now if you are given two rate constant, what is the expression? Log of K2 by K1 equals to equals to activation energy by 2.303 R into 1 by, if 2 is there, you'll write 1 minus. Clear? Simple calculation, nothing else. This is given, all the values are given, only EA is missing. You need to calculate EA. Now what? I'll just substitute the values. K2 is 2K. K1 is K. Equals to EA by 2.303 times 8.314 into 1 by T1 minus 1 by T2. 1 by 293 minus 1 by 303. Okay, now you are better at calculation, much better than me, and you will have to be faster also. The answer will come out to be 34,700 joule per mole. This is the answer. Now I'll convert it into kilojoule. That will be 34.7 kilojoule per mole. Clear? Okay. 34.7 kilojoule per mole. Correct. Samshik also answered correctly. Nagraj also answered correctly. Pooja answered correctly. Nalen, you also answered correctly. Okay. What was your question, Ramaya? KC didn't get KC30 course. It's actually KC90 have KC30 also. KC30 course. The course is a little slight variation is there. For KC90, you are getting ABHYAS test series also, and the KC30, I don't know exactly. The material may be a little different. I will get back to it now, don't worry. I will get back to you. Okay. Ma'am, if this chapter has high weightage, yes, electrochemistry, the chapters that I am doing from the last live, solutions, electrochemistry, then we have chemical kinetics, coordination, high weightage chapters. These all are high weightage. Alcohol, phenol, ether, aldehyde, ketone, carboxylic acid, the next one, it is also very high weightage. Then we have amines, biomolecules, they are also high weightage. They all comes, all the PU2 chapters are high weightage chapters. Okay. Okay, nice. Okay, let's do the next question. Match the following. Very easy, right? I'll just write the expression here. Mole raised to power 1 minus n, liter raised to power n minus 1, second inverse. For first order, the rate is second inverse. For first order reaction, the rate is second inverse. Now, which option has A1? A1. Only one option have A1. Did I do something incorrectly? Rate of first order reaction. Yes, it is second inverse. Oh, sorry. I misread it. You'll also do it the same way. Okay. Rate of first order reaction, rate of first order, second order, third order, any order reaction, rate will always be equal to mole liter inverse second inverse. Rate will always be equal to mole liter inverse second inverse. Okay, so the answer is mole liter inverse second inverse for A. For A, the option is 2. So we have 3 options, A, B and D. B, using B can we differentiate? We cannot, because all the B are same. So let's see C, option C. Okay, rate constant of second order. For second order reaction, if I put N equals to 2, the equation becomes mole minus 1 liter raised to power 1 liter second inverse. This will be your expression which resembles that. 4 resembles that. So C4, this is your correct answer. Option A. Clear? Option A, not C. No, not C. Option A. Now, how many of you answered option A? Let's see. Oh, 100. Option C is not correct. Why? Because rate, the list says rate of first order. It is not saying rate constant. Rate constant is second inverse. That is correct. But rate of first order reaction is mole liter inverse second inverse. That is the unit of rate. Unit of rate is rate. This is the unit of rate. That is the unit of rate. Okay? A option. Correct. Next question. If in an first order reaction the concentration is reduced from 0.6 to 0.2 in 5 minutes, the rate constant you need to find. You need to find the rate constant. So what is given? First order reaction, okay, and initial concentration is given. Initial concentration is 0.6 and the concentration after reduction, what is left, is 0.2 mole inverse. Time is also given in 5 minutes. Now it is in minute, but the answer is in seconds, so I'll convert it into seconds. 300 seconds. The rate constant you need to find, all the values are given. We know the expression, KT equals to 2.303 log of A naught by A. This is the expression. A naught we know, A we know, A naught we know, A we know, and T we also know, K only we don't know. So we'll put all the values here. K will be 2.303 by 300 times log of 0.6 by 0.2. If you calculate it, the answer will come out to be 3.66 times 10 raised to power minus 3 second inverse. How many of you answered C? How many of you answered C? Yes, I'll explain the first PU concepts when we'll solve PU1 questions, okay, which will be starting next week. Yeah, next week we'll be dealing with PU1 majorly. We take T2 minus T1, right formula. Yes, we take T2 minus T1. Yes, right in formula, option C. Still solving. Why? Yeah, solve. It's okay. Okay. Let me check the answer actually. The answer is for 3.66 times 10 raised to power minus 3 second inverse. So this is closest to your 3.62 times 10 raised to power minus 3. So the correct answer is option C. The correct answer is option C. Got it? Yes. Good. Pooja, it's not A. Recheck your calculations. You need to convert the unit. Unit conversion is very important. The minutes are in, the time is in minutes. You need to convert it into seconds. Rest all values are given to you. Don't worry. Okay? Yes, C. Correct. For question 12, how many of you answered? For 12, which was the question 12? The answer was A. Yes. 13. For 13, the answer is C. Okay. Now, let's move on to the next question. The rate constant for this reaction is this. Rate constant is given. From the rate constant, we have an idea that the reaction is first order. Why? Because the unit is second inverse. So the reaction is first order. Rate is also given. Okay, we are given K, which is 3 times 10 raised to power minus 5 second inverse. We are also given rate, which is 2.4 times 10 raised to power minus 5 mole liter inverse second inverse. Sorry for the bad handwriting. If you are not able to understand it, I'll write it clearly. That's why I write little slow. Rate equals to 2.4 times 10 raised to power minus 5 mole liter inverse second inverse. Then concentration of N2O5. First order. it's not given which order reaction is there, but we know from the unit of rate constant that the reaction is first order. And for first order, the rate law is what? Rate equals to K, rate constant for first order, times the reactant concentration. Reactant concentration. That is our rate law for first order reaction. That is our rate law for first order reaction. Can you explain step by step to solve last question? Noor, are you talking about question 13? Are you talking about question 13? If yes, then I'll answer it, don't worry. Okay. Now, firstly, let's solve this question. So, we know that from the rate constant, the reaction is first order reaction, right? Now, for first order reaction, the rate law is written like this. Rate is given, K is also given, N2O5 you need to calculate. Okay. So, that means N2O5 concentration. This is the question. Then the concentration of N2O5. This is the question. Okay. That is equals to rate by K. What is rate? 2.4 times 10 raised to power minus 5 upon 3 times 10 raised to power minus 5 will come out to be 0.8 mole liter inverse. 0.8. Option B. How many of you answered option B? Before 14, 13 she is asking, I think. 3. Correct. Option C. The answer is not 3. Option B, 0.8. My apologies. Okay, no worries. C. Okay. I hope if this question is clear, I'll just explain the first question, the previous question. Rate constant, from the unit of rate constant, we figured out if the reaction, what is the order of the reaction? The reaction is first order. Rate is given, rate constant is given. For first order, the rate law is like this. Rate is equals to K times reactant concentration raised to power 1. The reactant is N2O5. That's the concentration we need. So how will you determine the concentration? By putting the values, dividing them. Simple calculation is there. Okay? Am I not audible? Okay. Let's move on to the previous question. If first order reaction, it's AN actually. If a first order reaction, in a first order reaction, the concentration is reduced from 0.6 to 0.2. That means the initial concentration is 0.6 and now the concentration is 0.2. In 5 minutes, the time is 5 minutes. Okay. You need to find the rate constant. First order reaction. For first order reaction, we know the rate law. If we solve it, the equation comes out to be this. Hold on a second. Okay. Noor, right? Sometimes you won't remember the formula. What you do, you write the data and then you know one formula for first order. For first order, the equation is like this. A equals to A naught e raised to power minus K1 T, right? This is the expression. This is the expression to calculate the rate constant, to concentration or time. One data will be missing and rest all the data will be given. Here concentrations are given. Initial concentration is given. Final concentration is given. Time is also given. Okay. We need an equation where we can fit all that data and calculate the rate constant. Okay. Now, if you don't remember this formula, by some mishap, you don't remember it. So, you can just calculate from here also. You just rearrange these and get the formula. How? ln of A will be equals to ln of A naught minus K1 T. Clear? Till here it's clear, right? Now, if I just rearrange it, if I take it on the left hand side, K1 T will be equals to ln of A naught. It goes that side, minus ln of A naught minus ln of A, that means ln of M minus ln of N, that is ln of M upon ln of M upon N, right? Ln of M minus ln of N will be equals to ln of M by N. I hope that is clear. Basic logarithm formula, maths. Okay. This is equals to this. I want to convert this natural logarithm into log to the base 10. So what I'll do? K1T will be equals to, I'll multiply this by 2.303. 2.303 log of A naught by A. A naught is the initial concentration. A is the concentration at any instant, the instant we are calculating. Okay. A naught is 0.6, A is 0.2, T is 300 seconds, right? Only K is unknown and we need to find the K only, right? So I substituted everything here, and if I calculate it, log 3 value is somehow around 477, 0.477, okay? Noor, that's not a math class, it's a chemistry class, okay? Calculation step by step I have explained you. If you want, see, I'm not saying maybe you are weak in calculation, go to Ankit sir class, take maths class. This is not maths class, this is chemistry class, okay? I solved it by hand, that's why I'm telling you the answer. I solved it by hand only, okay? You do it for yourself. Log 3 is there, 0.4, simple calculation is there. I'm not doing that, okay? Just solve it by your hand only, okay? There'll be much tougher calculation in KCET if you're preparing for that. Yeah. Logbook is not allowed, but you remember log 1, log 2, log 3, log 4 value, that's more than enough. Max log 5. No one is going to ask you more than log 5, okay? No, I won't. I will be explaining next chapter also. Yes, there are classes every day. In the evening also there are classes, in the morning also there are classes. How to find the log value? Darshan, very nice question. Remember it. You don't have to find the log value. Remember it. Just write here only. Right now. Log 1 is 0. Log 2 is 0.30. 1 if you want to remember, don't. 0.3 is also fine. Log 3 is 0.47. Log 4 is 0.60. And log 5 is 0.69. It's not hard. I have memorized it. You see, you can memorize it too. Okay, next question. This I have done. And the next one. Half-life period of a first order reaction is 60 minutes. What percentage will be left over after 240 minutes? So I have explained the log method, very easy. So how many half-lives will be there? If one half-life is of 60 minutes and the total time is 240 minutes. So number of half-lives is 240 by 60. That is 4 half-lives. How many half-lives? 4 half-lives. Same formula to determine the concentration left at any point, that is equals to initial concentration divided by 2 raised to power n. N is the number of half-lives. N is the number of half-lives. How many half-lives we have? 4. Now we don't know the initial concentration. Don't know. We have the idea here. 100%. The initial concentration is 100%. So what will be your answer? 100 by 2 raised to power 4, which is 100 by 16, right? And if you calculate it, what will be your answer? 6.25%. 6.25%. Very easy, simple calculation. B. Yes. Darshan, why you are answering 3? B. Yes, correct. Okay. Log 5 0.69. Log 5 0.699. Okay. Now, you can also clearly, if it's 0.699, you can say 0.7 also. That will also work. Approximation you use. But remember, when you are going in your exam, remember at least till log 1, log 2, log 3. Log 1 is 0. You don't have to remember. Log 2, log 3, log 4 and log 5. These 4 values, just memorize them. Very easy. Okay, even if you memorize it to 1 decimal point, 0.3, 0.6, 0.4, okay, that is more than enough. You will get an idea. B. Calculator is not allowed in exam. Yeah, obviously it's not allowed. It's not allowed in exams, okay, KCET exams. Okay. C. Swati, your answer is C. How is it coming? C. 100 divided by 16, 6.25, no? It's not 6. Why? Calculator is not allowed. That's on the authorities. I can't answer that, no? Okay, next question. 1 liter of 2mCH3COH acetic acid is mixed with 1 liter of 3m alcohol to form an ester. You know, right? There is a reaction, esterification, when acid combines with alcohol. An ester is formed. This is the ester, right? Now, 1 liter of 2m and 1 liter of 3m alcohol. They form an ester. The rate of the reaction with respect to the initial rate when each solution is diluted with an equal volume of water. When each solution is diluted with an equal volume of water. Yep, the answer is, most of you are answering B. Why B? Yeah, I'm not tired actually. It's just, thank you for worrying though, but no, I'm not tired. Yeah. A, B. Let's solve this question first. So we are given CH3COH, 2m of CH3COH is dissolved in 2 molar is dissolved in 1 liter. Similarly, 3 molar of alcohol is dissolved in 1 liter. How much, what will be the concentration? No, how many will be the number of moles? Yes, number of moles we can find, right? Okay, for acetic acid, number of moles for acetic acid. Okay, we have the, right? How do you calculate it? Molarity equals to number of moles per unit volume. Volume is given, molarity is given, number of moles will be molarity times volume, which is 2 times 1. 2 moles of acetic acid is there. Okay, how many moles of alcohol is there? We have 3 molar alcohol in 1 liter of solution, so that is 3 mole. So now we know how many moles of acetic acid are there and how many moles of alcohol are there, ethanol are there. Okay, the question is asking initial rate. What is the initial rate? What is rate? Concentration of ethanol times concentration of acetic acid. Concentration, we have the number of moles. We have the number of moles. Can we calculate the concentration? Concentration is what? Number of moles. Concentration is number of moles per unit volume. How much is the volume of solution? 1 liter of this is mixed with 1 liter of that, so that means 2 liter. Volume is 2 liter. Volume is 2 liter. Number of moles we know. Okay, so let's calculate for alcohol first. Okay, for alcohol, the concentration is what? The concentration is number of moles per unit volume. Number of moles for alcohol is how much? 3 moles. Volume is how much? 2 liter, because 1 liter of this is mixed with 1 liter. This is the calculation we are doing for initial rate. This is the calculation we are doing for initial rate. Okay, now let's see. This is 1.5. Similarly, for your acetic acid. For acetic acid, the concentration is number of moles. How many moles? 2 moles. 2 moles. Total volume is how much? 2 liter. So that means 1. This is the concentration. These are your concentrations. Okay. This is the concentration, 1.5 and 1. So what will be the rate? What will be the initial rate? Rate will be equal to K times concentration of alcohol. How much is the concentration of alcohol? 1.5 times concentration of acetic acid. How much is the concentration? 1.5 K. 1.5 K. That is the initial rate. Now, if we are adding equal volume of water, what will be the changed rate? So the question is simple. Initially, let's say the rate was R. After diluting the solution, when you add more volume to the solution, what will be the new rate? Okay, what will be the new rate in respect to this initial rate? Ratio it's asking, right? What will be the new rate in respect to the old rate? So that means it is asking for the ratio. Okay, very simple. Option 3, no, it's not correct. Okay, now let's see. This is the calculation we did for initial rate. Initial rate came out to be 1.5 K. Now if we calculate for after dilution, we are diluting it, okay, but with equal volume of water. We are diluting it but with equal volume of water. Let's say I added 1 liter of water to this, 1 liter of water to acetic acid and 1 liter of water to ethanol. Both I added 1 liter. Okay, now what will be the concentration? Let me just write. Rn is your new rate. New rate will be equal to K times the concentration of ethanol. It changed. Why? Because the total volume changed. How? What is the total volume now? 1 plus 1, 1 plus 1, 2 and 2, 4 liter. The new volume is 4 liter, right? But the number of moles are still the same. Why? Because see, number of moles are still the same. Why? Because the concentration is same. Number of moles will be same only. So for C2H5OH, okay, for C2H5OH, this is after dilution. After dilution, for C2H5OH, for ethanol, the concentration is number of moles, which were 3, by total volume. In this case, the total volume is 4 liter. The total volume is 4 liter. 4 liter. 3, yes, 3 by 4, correct. 0.75. Okay, done. For acetic acid, now for acetic acid, what will be the concentration for acetic acid? It will be number of moles of acetic acid 2 by total volume, which is 0.5. The new rate will be concentration of ethanol, which is 0.75, times concentration of acetic acid, which is 0.5. You need to find the ratio, the rate of the reaction with respect to the initial rate. Rate of the reaction with respect to the initial rate. So we are asked rate of the reaction with respect to the initial rate. This is the initial rate. R is the initial rate. How much? Rn is equals to K times 0.75 times 0.5 by R, which is 1.5 K. Okay, if I just solve it, 1.553 and it will come out to be 0.25. New rate is 0.25 times of the original rate. Okay, if I take it this side, I can also write new rate equals to 0.25 times of the original rate. 0.25 times of the original rate. Okay. A. Yes, so the answer is A. I know it looks a little messy, but it's very easy. So initially we have 1 liter of acetic acid, 1 liter of ethanol, okay, and the reaction is happening between the 1 liter only. The rate will be equal to the concentration of both. It will be the product of concentration of ethanol and acetic acid. We needed the concentration. How did we calculate the concentration? Number of moles per unit volume. Volume is the total volume. Here the volume was 2 liter. Okay. Number of moles, 2m in 1 liter. Number of moles is molarity. Molarity times the volume. Okay. So 2 moles of acetic acid and 3 moles of alcohol are there. Okay. We divided these moles by the total volume. For the original case, without dilution one, the first case, that was 2 liter, okay. The answer came out to be 1.5 for ethanol, for 1 for acetic acid. We calculated the rate, which comes out to be 1.5 K. This is your original rate. When you did dilution, so you added equal amount of water. So let's say I added 1 liter to acetic acid, 1 liter to ethanol, okay. Number of moles are still the same. Why? Because obviously no alteration with concentration, it's still the same, okay. Now, the concentration, the new concentration after dilution, the new concentration will be what? Number of moles per unit volume, number of moles per unit volume, yeah. In this case, the total volume became 4 liter because we added 2 liter though we had, right? And we added 2 more liters, right? So it became 4 liter. So that's how we calculated the concentration for ethanol and for acetic acid, and we substituted these values in this rate expression, and that's how we find the new rate. And what did we need? We needed the relation between the new rate and the original rate. So we took the ratio. The answer came out to be 0.25. So that means the new rate is 0.25 times of the initial rate. New rate is 0.25 times of the initial rate. Okay, you missed a decimal point. Yeah, don't miss that in your exam. If you miss it now, it's okay. Okay, but don't miss it now, later in your exam. I think, yes, we'll start coordination now. Okay, let's start coordination compounds. Now we'll see how fast you can answer. Okay, I'm actually looking at your comments now. Okay. Hi, I'm here only. Let's start with the question first. Am I audible now? So, why there is no sound? I hope now the sound is coming. How many questions? You tell me, FRP, you count it, okay? You tell me how many questions are there. Okay, there is sound. Yes. Okay, now let's start with the question first. Are you guys liking the session? If you are understanding, if you are able to solve the question, if you are, if you are understanding, please like the session, okay? The question is on treating 100 ml of 0.1 m aqueous solution of this complex with excess of AgNO3, 2.86 gram of AgCl was obtained. The complex is. Okay, so the complex is what? Firstly, we'll calculate how many moles of AgCl we are getting. Let's calculate that first. Oh, thank you so much. Okay. So firstly, let's calculate the moles of AgCl. 2.86 gram is the amount that we are getting. 2.86 gram is the amount of AgCl that we are getting. Okay, how do you calculate moles? Given weight by molecular weight. Given weight divided by molecular weight. 2.86 divided by how much for AgCl? 108, 35.5. That will be 143.5. Okay, 143.5. If I calculate it, it's comes out closer to be 0.02 minus 1 0.02. Okay. This is the number of moles of AgCl that are produced by this complex. Okay, how many moles of this complex are there? How many moles of this complex are there? So again, moles are simply how you calculate moles, concentration times volume. How much is the concentration of this complex? Moles of complex. How much is the concentration? 0.1 m. Clear? That is the concentration. Okay. Volume. The volume is 100 milliliter. 100 milliliter. We'll convert it into liter, minus 3. Okay, the answer will be 10 raised to power minus 2, which is 0.01 moles. These are the number of moles of complex, 0.01, and we are getting 0.02 moles of AgCl. We are getting 0.02 moles of AgCl. Third option, yes. So we are getting this much moles. This is the complex and we are getting this much moles. So we'll calculate how many chloride ions are we getting. How many chloride ions we are getting. Okay. So number of ionizable chloride ions will be moles of AgCl divided by moles of total moles of complex. So we have 0.01 moles of complex. We are getting 0.02 moles of AgCl. So how many ionizable chloride ions are there? That are 2. That means there are 2 chloride ions there that are ionizable. Okay, that are ionizable. Okay. Now see, number of chloride ions we are getting 2. Okay, so that means you have one thing, right? In coordination compounds, you have a coordination sphere. This is your coordination sphere. And outside the coordination sphere, there is an ionizable ion. Ionizable ion. Okay, ionizable ion, this is the ionizable part. You can ionize them, right? You can form, like they can, you can convert them into ions, but this is the non-ionizable part. It doesn't break down. It stays as whole only. Okay, so we are getting 2 chloride ions. Number of ionizable ions is 2 chloride ions. Okay, so what will happen? That means here 2 chloride ions are there. Here 2 chloride ions are outside the coordination sphere, because only if they are outside the coordination sphere they will get ionized. Okay, inside the coordination sphere nothing happens. It stays as whole only. Okay, so there are 2 chloride ions outside. Now we have 3 chloride ions and 6 water molecules, and chromium forms actually 6 only. 6 bonds only. Okay, it is octahedral, it forms 6 bonds only. So what will happen? We'll try to arrange it. Chromium, inside there will be, let's say, 5 hydrogen and 1 chlorine, because if that all the chlorines were outside, we would have gotten 3 AgCl. We would have gotten 3 AgCl, but we only got 2. That means only 2 chloride ions are outside, and that other third chloride ion is present inside the coordination sphere. The third chloride ion is present inside the coordination sphere. Okay. Oh, sorry. Okay, so this will look like Cl2.H2O. One water molecule is also there, right? Where will that water molecule go? Outside the coordination sphere. That water molecule will go outside the coordination sphere. So this will be the formula of the complex. We calculated the moles of AgCl. We calculated the moles of the complex. Now 0.01 moles of complex is giving 0.02 moles of AgCl. So how many chloride ions are there? 2 chloride ions are there. So that means these 2 chloride ions are a part of the ionizable part. They are a part of the ionizable part. Okay, so that means 2 chloride ions are outside, rest will be inside. But we know chromium will only form 6 bonds, octahedral complex, right? So we did 5 water and 1 chlorine. 1 water molecule will be left, that will also be present outside. That will also be present outside. How it came, ma'am? Hina, right? AgCl, that is the molecular mass of AgCl. AgCl's molecular mass is 143.5. Silver's atomic mass is what? 108. And chlorine is 35.5. I added those and the answer came out to be 143.5. Number of moles is given weight upon molecular weight, right? So that is the molecular weight of AgCl. And in this case, we didn't need the molecular weight. Why? Because there is one more method to calculate number of moles. We know molarity equals to number of moles per unit volume. If molarity is given, volume is given, we can calculate the number of moles. So for complex, we used this method, and for AgCl, we used this other method. Okay. Okay, I hope, Hina, your doubt is clear. Okay, next question. In the complex ion, the coordination number of iron is, what is this? This is oxalate ion, right? C2O4. What is this? This is oxalate ion, right? And what is it? It is a bidentate ligand. This is oxalate ion actually. Okay, this is oxalate ion. It has 2 donor atoms, 2 donor sites actually. Okay, so that's why it's a bidentate ligand. I hope I'm not saying some fancy words to you, because bidentate ligand, then I'll say denticity. Denticity is the number of donor atoms that are present on a ligand. That are the number of donor atoms from which it can form the bond. That is denticity. Okay. They are not foreign words. You might have heard it in your coordination compound chapter. Okay. So I hope I'm not saying anything weird to you. Okay. Bidentate ligands. So in this complex, this is a bidentate ligand. Oxalate ion is a bidentate ligand. That means it forms bond from both these oxygens. Now whenever you are calculating the coordination number, the formula is really simple. The coordination number is equals to the number of atoms times number of atoms of ligand. Number of ligands. How many ligands are here? 3 ligands are here. Coordination number equals to number of ligands. 3 ligands are here times the denticity. Denticity means how many donor atoms are there, how many donor atoms are forming the bond with the central metal atom. How many donor atoms of the ligands are forming bond with the donor atoms. So here 2 atoms are there. 2 donor of this ligand, 2 atoms are there that are forming the bond. So the denticity is 2. The denticity is 2. The coordination number will be 6. The coordination number is 6. Correct. Question 1. You answered A, B, C. Only 23% answered C. Question 1's answer was C only, right? Okay. Okay. So the correct answer is, the evening class is at 5. Okay, the evening class will begin at 5 p.m. The coordination number is 6. An additional question for you. What is the oxidation state? What is the oxidation state of iron here? What is the oxidation number of iron? What is the oxidation number of iron? Oxidation state or oxidation number of iron? Three. Plus 3 minus 3. Ma'am, if I do this, is it enough? Advait, if you are present in all the classes, if you are studying every day properly, That means you are studying only KCET related. You are solving the questions. You are giving mock test. You are doing revision. You are disciplined. Then yes, you can. But if you're just totally relying on other people, like I'm teaching you, you're relying on me, that's nice. But after this class ends, you need to sit down and solve these questions on your own. You need to revise the chapters on your own. If you do not do that, then this the whole hard work that we all are putting in, that's going to go waste. Okay, so yes, you can do it if you study, if you focus and work hard. +3. Okay, done. Yes, it is +3. Why? Because C2O4, it has a charge of -2. It has a charge of -2. And if, let's suppose, the oxidation state of iron is X, plus 3 oxalate ions are there, and each has a charge of -2, and the overall charge of compound, overall charge on the compound is -3. So X will be equals to +3. Clear? That is the oxidation state. Okay. Morning class time is 9. Okay. Today it was a little late, but normally it's 9, and the evening class is 5. 9 a.m. and 5 p.m. Okay. 5 to that I don't know. Homolaptic complexes. Homolaptic complexes among the following. Now, what are homolaptic complexes? Homolaptic complexes are those complexes. Homolaptic complexes are those complexes in which the metal atom is bonded to only one type of ligands. In which the metal atom is bonded to only one type of ligands. Okay. These are your homolaptic complexes. When all the any one I can take actually. Okay. When the central metal atom is bonded to only one type of ligands, only one type of ligand. All here the ligand is water, and all the 6 ligands are water. They are only one type of ligand. That is your homolaptic complex. Okay, that depends on the type of ligand. If there are more than one type of ligand, then that will become a heterolaptic complex. Heterolaptic. For example, here only this will be an heterolaptic complex. Heterolaptic, right? When more than one type of ligands are there, more than one type of ligand or different type of ligand. One type of ligand attached to central metal atom. Central atom. Okay. So the answer is, let's see, aluminum. Aluminum is connected to only oxalate, one type of ligand, oxalate only. Okay, so yes, this is a homolaptic complex. This is a homolaptic complex. Cobalt has 2 type of ligands, chlorine and ethylene diamine. Chlorine and ethylene diamine, both are different ligands. Okay, so that means it is not a homolaptic complex, it is a heterolaptic complex. Zinc is only connected to hydroxide. Zinc is only connected to one type of ligand, that is hydroxide. So that is also a homolaptic complex. That is also a homolaptic complex. So you have 1 and 3. Option C. Let's see how many of you answered option C. Yes. So yes, 80% of you answered option C. Okay. C. Okay. C. Correct. Okay. Yes. Done. Yes, so the correct answer is option C. Homolaptic complexes are those complexes in which all the ligands are same. The central metal atom is attached to only one type of ligand, that is homolaptic complex. Heterolaptic complexes are those complexes in which the central metal atom is attached to more than one type of ligands, different type of ligands or more than one type of ligands. That is heterolaptic complexes. Similarly, we have homonuclear, heteronuclear also, right? Okay. The coordination number and the oxidation state of M in this complex. Coordination number, let's start with the coordination number. Now see, if it is written like this, so this is the cationic part. That means it is acting as the cation here, and this is your anion. Clear? I hope it is clear. If it is written like that and some ion is written beyond it, normally when you are writing any coordination compound, first you write the cation, then you write the anion. First you write the cation, then you write the anion. Okay. So let's figure out the coordination number first. For ethylene diamine, again, the density, the ethylene diamine, the density is 2. The density is 2. Ethylene diamine forms bond by these two nitrogens. Both of these two nitrogens donate. Okay. So the density, the number of donor atoms that are donating to the central atom, they are 2. Okay. So coordination number will be number of ligands. Number of ligands is 2, and the density is also 2 for ethylene diamine. This is ethylene diamine. Okay. Plus oxalate, we just did it. Oxalate has a density of 2, and how many oxalate are here? 1. So that means the coordination number is 6. The coordination number is 6. This is the coordination number. What is coordination number? Number of ligands times density. Number of ligands times density. That is your coordination number. Now oxidation state also asked. Oxidation state. Okay. I told you this is the cation, right? And this is the anion. This is the anion. Nitrito we call it, right? So nitrito has a charge of -1. Nitrito has a charge of -1. So that means if it has a charge of -1 and here it is showing no charge, it is neutral here, that means +1 charge will be coming from here. +1 -1, the compound is neutral. Because you see there is no charge on this overall compound, right? So that means here the charge is, this cationic part has a charge of +1 and this anionic part has a charge of -1. Okay, now I'll calculate the oxidation state for M. X, let's say the oxidation state is X plus ethylene diamine has no charge. Ethylene diamine is a neutral ligand, it has no charge. Okay. C2O4, yes, oxalate has charge. How much? -2. How many oxalate are there? 1. 1 times -2 equals to the overall charge of the compound. Overall charge of the compound is +1. The overall charge is +1. Okay. So that means the oxidation state of the M metal is +1 +2, which is +3. Which is +3. So 6 and 3. That means option C. You guys are a little confused. 6 and 2, 6 and 3. Google. Okay. C, A is not the answer. 2 is not. Why not 2? Because we know this nitrito, the name is nitrito. Okay. NO2 has a charge of -1. Okay. To neutralize that -1, this cation must have a charge of +1. Only then they will be neutral. +1 -1. Okay. So then, yes. So the overall charge is +1 on this compound, on this coordination compound, and that ene has no charge, 0. So we won't calculate it, we won't add it in the calculation. Oxalate has a charge of -2, +1 times -2 equals to +1, and X will be equal to +3. Okay. Is it clear? The answer is option C. The answer is option C. For question number 4, yes, option C. Yeah, 51% are answering option C. A is not correct again. Okay. Tell me the type of isomerism that is existing here. Just give me 2 minutes break, I'll be back. Okay, I'll just write here. No, 5 minutes is not required. I'll be back in 2 minutes. Hello. Sorry for the delay. Okay, I hope I won't be taking any more. Okay, I'll complete this chapter now. Okay, you should also be ready because you guys need to answer along me. Yes, okay. Let's start. So the question is the complex compounds, what kind of relation is between these two compounds? Okay, so let's just see the relation first. They are isomers. They are isomers as they have same molecular formula. Guys, be ready. Okay, we have so many questions to go. How's the Josh? D ma'am. Yes, D. Yeah, ionization isomers. Oh, I took 5 minutes. Oh, you were timing it? Were you timing it? Okay. Sorry if I took more than the said time. Yeah. Okay. Fine. Hi ma'am. Hi everyone. Oh, it's not an issue. Oh, thank you. Answer this question first. Okay, so we have these two complex compounds. They are looking quite similar, right? But the only difference is in the ions between the coordination sphere and the ionization ions. Okay, the outside ionization, what do you call it, that the outside ions and the coordination ions. The outside ions and the coordination ions, only the difference is there. Thank you. Hi Varun. Okay. Hi Sunita. Hi everyone. Okay, so let's focus on the question for now. Any doubt you have, do ask me when I am looking at your comments. Okay, and at the end of the class I'll definitely take your doubts, any doubt you have. One doubt I remember, I'll answer that in one doubt session. One of the kids asked. Okay, please fast ma'am. Yes, where are you running? Slow, you haven't read the story. Slow and steady wins the race. Keep it to every day, be consistent. Okay, yeah. Okay, so these two complexes, what kind of relation they show? They are ionization isomers, we know, but just by looking at them. But a coordination isomers, coordinations, you have two. You have a cationic part and you have an anionic part, and there is an exchange of ligands between the cationic and the anionic part. Both are complexes. One is cationic complex and one is the anionic complex, right? And there will be an exchange of ligands between the cationic and anionic complex. That is coordination isomers. Okay, that is not shown here because as you see, the ligands are almost the same. Only one ion is getting exchanged between the outside and the coordination sphere. Optical isomers, non-superimposable mirror images of each other. They are not, nothing such as such, because all the atoms are same here. They won't be making optical isomers. Geometrical isomers, cis-trans isomerism. Do you have cis-trans? No. These kind of MA5B, they don't show geometrical isomerism either. Okay. Okay, right? So we are left with ionization isomers. The ionization isomers, there's one more isomerism which is similar to ionization, solvate isomerism or hydrate isomerism, right? Both are same. Solvate means solvent is there, and if the solvent is water, hydrate. That is similar to ionization. There is the exchange of water molecules in that case. Here there is the exchange of ions, right? See, there is exchange of ions between bromine and sulfate. Here also sulfate and bromine. So if you add here Ag nitrate, silver nitrate in this one, you will get a ppt of silver bromide. Okay, here if you add barium chloride in this one, in this solution, if you add barium chloride, you will get a precipitate of barium sulfate. That's how we know that different atoms are present, different ions are present outside the coordination sphere. Okay, and that is a type of isomer, ionization isomer. What is that type? It is called ionization isomers. Okay. Pallavi, count with me. We are on 5th question. I am solving the next one. Okay. How many questions are there? You tell me by the end of this class. Okay. Some 20 who are guessing 20. Which formula and name combination is incorrect? Incorrect. You need to find the incorrect. So I need to explain the nomenclature rules here. We know that there is cation is written before the anion, right? And the whole name is written in continuation. The whole name is written in continuation. Pallavi, will you count? You will count, right? Okay. The whole name is written in continuation. Okay. Now, when we are looking at the name, for example, in this one, we start from the cation first. Here the cation is potassium, correct? Okay. After that, you name this coordination sphere. In coordination sphere, you name by alphabetically. Firstly, you start with ligand. which has the alphabetical order, then the second ligand which comes later in the alphabets, okay, and then after that you name the metal, okay. If one thing, if your metal is present in the anionic sphere, if your metal is present in the anionic sphere, here it is the part of anion, right? It is the part of anion. If your metal is present in anionic sphere, you add an 8 in the end. You add an 8 to the metal in the end. You add an 8 to the metal in the end. If your metal is the part of neutral complex, for example in this one it's a whole single complex, neutral complex, no charge there, in that case, and if the metal is a part of the cationic part, cation and neutral, if metal basically the coordination sphere is a part of cationic part or the neutral one, when the whole compound is neutral like this, okay. In that case the metal name is written regularly. Okay, regularly like platinum you write, okay. And then obviously after writing the metal you write the oxidation state in brackets. Oh, I'll talk in Hindi, don't worry. By the end of the class, I'll talk, okay? Right now, we are solving questions. Yeah, RCB. You should study if your KCET is coming really close. Why are you going to RCB and all? Match will be there. You can watch the highlights later on. Okay. So, let's start with the first one. Potassium. Trioxylato, yes, when anion is there, whenever any anion is there, you add an O at the end. Oxalato, okay, trioxylato. Aluminate बनेगा. यहाँ पे the aluminum, here the aluminum will become aluminate. Why? Because as I told you, this is the part of anion, and if your coordination sphere is the part of anion, at the end of the metal name you add an 8. Okay? Aluminate. Clear? And the oxidation state is 3, which is correct. If you calculate here also, the oxidation state will comes out to be 3 only, right? -2 times 3 minus 6, and the whole charge is -3. Equals to -3 plus 6 will be +3. That's the calculation I did for oxidation state. Okay, not needed here. Okay, next one. In this case, you start with which amine come first. So diamine, this di, tri, tetra, bis, tris, tetrakis, they are not considered while you are looking alphabetically at the ligands. When you are considering the naming in alphabetical order, this di, tri, tetra, they are not taken in consideration. Because you would say D comes after C, ma'am. Why did you write chlorido first? So that simple explanation, we are looking at amine only. Okay. First priority is RCB match. Yo, bad person. No, don't do that. Bad bacha. Diamine chlorido. So the name is diamine. Then you write chlorido again, because after AC comes, and this NO2 is nitrito. The NO2 is nitrito, okay, and since it is connected by nitrogen side, we show nitrito N. If it is connected from oxygen side, then you call it nitrito O. But here it is connected from nitrogen side, that's how we call it nitrito N. Now this whole complex is one single unit and neutral. There is no charge. It's not the part of cation, it's not the part of anion, it's a neutral complex. Okay, so you write platinum and then the oxidation state of platinum, which is 2 here. Okay, which will be 2 here. Okay, this one dichlorido, bis. Okay, for ene or any other complex ligands, we don't use di, tri, tetra. What do we use? Bis, tris, tetrakis. Bis, tris, tetrakis. Okay. bis, tris, tetrakis. That's not how you behave in class. That's not nice, Akash. Okay. So here, instead of this di, there should be bis ethylene diamine. Okay, that's one error we have in the name. That means this name is incorrect. But if you go out also, you see cobalt, the oxidation state is also wrong. The oxidation state is also wrong. The oxidation state is X minus 2 equals to plus 1. X will be equals to plus 3, not 2. The oxidation state of cobalt is plus 3, not 2. The oxidation state of cobalt is plus 3, not 2. So the incorrect name is this one. What should be the correct name of this? Tell me the correct name of this. C. Yes, C is the incorrect one, but what is the correct name of this? Okay, I'll write here only. The correct name will be dichlorido bis ethylene diamine bis ethylene diamine cobalt 3. The oxidation state is 3. You write it in brackets, chloride. Chloride. Okay, that is the correct name. Dichlorido bis ethylene diamine cobalt 3 chloride. That will be the correct name. And this is also correct. Tetraamine, aqua, tetraamine. Then you have aqua, chlorido, cobalt 3 chloride. Cobalt 3 chloride. Okay, done. Beside no, that's not bis ethyl bis ethylene diamine. Bis ethylene diamine. Next question. The isomeristic name of this complex, very easy. What is this? It is the part of cation and it is the part of anion. So if your metal or if your coordination sphere is part of cation, the metal name will remain same. You won't write 8 at the end. It will be cobalt only. You see, I see some options here. Cobaltate. This is incorrect. Already incorrect. Okay. Carbonate. The anion is chloride, no? Not carbonate. So this is also incorrect. 2 options eliminated instantly. Okay. Now see here also. Okay. Now let's see. Carbonate starts with C. Amine starts with A. So A should come first, right? Pentaamine. Here it is carbonate pentaamine. So obviously this is incorrect. That will be your correct name. Okay. But we'll write it again. Other color while writing on board. Why? What is your favorite color? I'll use that color. Okay, tell me your favorite color. I'll use that color. Vena Lat, right? What's your name, Vane? Red. Is it visible? I asked for the person who said, ma'am, change the color of pen. Those people reply. Okay. Blue, yellow, my God. Whole rainbow coloring. Vibgyor is there. I'll use all the colors. Okay, I'll keep switching in between. Green. Oh, maroon. We don't have that much options here. Okay, we'll start there by writing the name. The name is pentaamine. Pentaamine. For carbonate, it's an anion. We write carbonato. Okay, I'll write it here. Yes, pentaamine. Then you have carbonate, so you write carbonato. Cobalt. Now this is the part of cation, so obviously the name will be regular name. You won't be adding 8 at the end. So name is cobalt. What is the oxidation state? Let's see. Chlorine has an oxidation state of -1. So that means this would have an overall charge of +1. Carbonate is what? X. This is X, the oxidation state of cobalt. Carbonate has a charge of -2. -2 equals to +1. That means +3 is the oxidation state of cobalt. +3 is the oxidation state of cobalt. Okay. Now pentaamine carbonato cobalt 3, and then chloride, Simple. Option A. We already guessed it using elimination, but we cross-checked it also. Okay. Green. Okay, let's move on to the game for you all. You are in class 10. I am teaching KCET portion. This is not class 10 portion. Okay, let's start with the colors then. Okay, next we'll take blue. Okay, next color is blue. Let's see if you can see it. It won't be visible, or is it? No, it's not visible. I'll take this one. Okay. The formula of penta aqua nitrato chromium 3 nitrate. Formula of, after blue we'll use yellow, and then we'll use, I'll try to use all the pens. Coffee, then at least, if no option, then black. Okay, tell me the answer of this one, no? Okay, tell me the answer. Hello? Maroon, okay, we'll see if we have maroon. We don't have maroon here, I think. Or we do. Oh, we do have. Yeah, it's gone. Okay, there was some error, I think. D, C, D, B. Okay, so many mixed opinion. Penta aqua nitrato chromium. So that means we have firstly what? Chromium. We know about that. I'll write here. We have chromium. Okay. Penta aqua means 5 water molecules are there. 5 water molecules are there. Nitrato is NO3. Okay. Chromium 3 nitrate. Chromium 3. That means chromium has an oxidation state of +3. Normally you say +3 only. Okay. Chromium has an oxidation state of +3. So how will we get +3? This is -1. This is -1. X -1. Water is neutral. It doesn't have any charge. Okay. Done. This is your cationic part. What will be the anion? Nitrate. But we don't know how many nitrate. Because this we need for the oxidation state. Okay, let's say X -1 should be equal to what number that the oxidation state comes out to be 3. So that means it should be equal to +2. It should be equal to +2. Only in that case the oxidation state will come out to be +3. Only in that case the oxidation state will come out to be +3. Okay, so that means how many nitrate will be there? 2 nitrate. 1 nitrate has a charge of -1. Okay, 2 nitrate will have a charge of -2. To balance this -2, there will be +2 here. Okay, on this cation +2. And that's how we get the 3 oxidation state. To satisfy the oxidation state, we'll figure out how many nitrate we need. Okay, because this part is specified simply. They give the correct numbering, how many are there for the coordination sphere. But ionization sphere is quite dynamic. You need to figure out on your own. Okay, so the correct answer is option C. How many of you C? I'm seeing. Yes. So many of you are answering C. Yes. Why are they all so close and all? Hey. Yes, guys, like the session. Okay. Okay. Yes, the correct answer is option C, not D. Swati, it's not D, it's C. Yes, so because we want to balance, this is not nitrato, this is nitrito. NO2 is nitrito. I know names are little bit confusing, but this is nitrito, not nitrato. Nitrato is NO3. It has a charge of -1. Okay? Okay, yo guys, yes, everyone like the session. If you are enjoying it, yes, if you are able to solve all these questions. Okay? Okay, next question. Yes, I do know. if a bidentate ligand, ethane 1,2-diamine, is progressively added to the molar ratio, it's a really nice question, okay? Little bit brain, little bit, your Vibgyor will come here, your rainbow, you all were telling your favorite colors, it will come here, okay? To this one aqueous solution following the coordination entities 1:1, 2:1, 3:1 in that ratio, okay? This is the compound and we are adding ethylene diamine to it, okay? So we have two ligands here, one is H2O, oh, I'll change the color, so difficult, let me, if I take something bright, it will be visible, right? Is it visible? No, it's not visible. Okay, we'll take something. Hey, I'm really bad at it. Okay. I hope it is visible, or else I'll take yellow only. Okay. So, the question is really nice actually. What are we given? We are given two ligands, H2O. I'll take yellow only, it's not working. Yep, it will work. We have two ligands, H2O and ethylene diamine. What is happening here? We are adding ethylene diamine to this complex, NiH2O 6 2 positive, right? Now, what will ethylene diamine do? It will replace the water molecule. If it will replace the water molecule, one thing we know that water is a weak filled ligand. Ethylene diamine is a strong filled ligand. This much information we have, okay? Water is a weak filled ligand, ethylene diamine is a strong filled ligand, okay? What is the difference? Strong filled ligand have high crystal filled splitting energy. Octahedral complex we are talking, so octahedral, this is the crystal filled splitting energy for octahedral complexes. So that means what? The crystal filled splitting energy for ethylene diamine is greater than that of water. That's what means by strong filled ligand and weak filled ligand, okay? Now, if the energy is high, this is energy, right? In place of this, I can write E also. How is energy and wavelength related? How is energy and wavelength related? Any one of you can answer me. How is energy and wavelength related? Energy and wavelength are inversely related. Energy and wavelength are inversely related. Clear? Energy and wavelength are inversely related. If energy is high, the wavelength will be low. Okay? We'll need that relation. That's why I told you that. Okay? We'll need that relation. So elimination thing that won't work on most of the question. Here it will work. I'll tell you how. So we know if we are replacing H2O with En, which is a strong filled ligand, the crystal field splitting energy will be high. That means the wavelength will be low. Why do I mean that? See, initially the ratio is 1:1 of ethylene diamine and nickel. Then it increased 2:1, then it increased 3:1. The amount of ethylene diamine is increasing. If amount of ethylene diamine is increasing, that means this energy is increasing. Energy is increasing, right? So when you are going from here to here, 1, 2, 3, what is happening? The crystal field splitting energy is increasing, right? Energy is increasing. That means the wavelength is decreasing. The wavelength is decreasing. Okay? The wavelength is decreasing. So one thing for sure, what is the one thing? That in between 1 and 3 will have lesser wavelength. 3 will have lesser wavelength and 1 will have higher wavelength. 1 will have longer wavelength and 3 will have shorter wavelength or lesser wavelength. Is it clear? If it is clear here, then you can eliminate options here. See, first is 300, second is 475. That is incorrect because 1 is supposed to have higher wavelength and this is supposed to have shorter wavelength, according to our this interpretation. So this is incorrect. Similarly for this also, the 310 for first and 500 for third, that is incorrect. Why? Because it should be greater for 1, it should be greater for this complex than this complex. Clear? If it is clear here, 2 options are eliminated and these 2 options are left. Okay. Now here comes a little remembering part. If you remember correctly, this much, this is the wavelength of UV visible, UV spectra. This comes in the UV range, and UV range is not visible at all. UV light is not visible at all, okay? And in this case, we are seeing some color. That means the light comes in the visible spectrum. That means the light is falling into the wavelength is falling into the visible spectrum of light, right? But if it is falling 310, it is UV range, right? In UV range, the wavelength, the light is no visibility is there. UV light you can't see, okay? So that means this is also incorrect. Okay, now one more thing I have for those students who don't remember this value. Okay, one more thing we can do. What? Okay, now see, you have this VIBGYOR. This is the rainbow, right? This is the visible sequence, visible light comes in this. So when you're going from violet to red, what is happening here? The wavelength is increasing. The wavelength is increasing. It has around 400. Violet color has a wavelength of 400, and red color has a wavelength of around 700 nanometer. 700 nanometer. So when you're going from violet to red, what is happening? 700 nanometer. The wavelength is increasing. Okay, I'm not trying to complicate it for you, so just listen carefully. Okay, wavelength is increasing. Now if the wavelength is increasing, see, look at the colors. These colors, remember one thing in chemistry, when you are seeing the colors that are seen by you, they are the complementary colors of the light that is being absorbed. They are the complementary colors. They are not the correct color. The compound absorbed a different wavelength light, absorbed a different colored light, and it gave a different complementary color. We have a complementary color wheel here. This is the complementary color wheel. Just one small wheel. Make 6 sections. 6, I think. 3, 6. Start with V, B, G, Y, O, R. Now see, the color that are present in front, the colors that are present in front are the complementary colors of each other. Complementary colors of, for red it's green, for blue it's orange. Clear? This is the color wheel. V, B, G, Y, O, R, Y, O, R. Okay. Now if you are seeing blue color, it is the complementary color of what? Blue is the complementary color of orange. That means the light that is absorbed by this compound is orange. That means the light that is absorbed by this compound is orange. Here you are seeing violet color, here you are seeing the violet color. So that means the light that is absorbed by this third compound is yellow. This is yellow. I'll write here. This is yellow. Clear? Orange and yellow. Okay. Now see here. Yellow, orange. That means orange have a greater wavelength than yellow. That means orange have a greater wavelength than yellow. Now you see, orange comes near 700. So this value should be around 600. I am taking this value should be around 600. And it should be less than 600. So 550 I am taking. Okay, around 550 let's say. Yellow is close but still lesser in wavelength, so it should be around 550. Okay, see the options here. 600, yes. This one, first wavelength is 600, and for the second wavelength is 500, 550, 530 close by. Clear? Just tell me if you understand it. Oh my god, you got confused. Okay, this is... Okay, I'll explain it again, but tell me if it is clear a little bit. Okay, see, what are we doing here actually? We have ethylene diamine, okay, and we have this compound, nickel compound, okay. What are we doing? We are adding ethylene diamine to it, okay, in the ratio this 1:1, 2:1, 3:1, and we made these 3 compounds. Now as you are going from 1 to 3, what you are seeing that more ethylene diamine molecules are there. 1, 2, 3 ethylene diamine molecules are there. We know that ethylene diamine is a strong filled ligand and water is a weak filled ligand. So we are doing what? We are replacing weak filled ligand by a strong filled ligand. If we are replacing it by a strong filled ligand, some things are there. What? Strong filled ligand have high crystal field splitting energy. We know that, right? If they have high crystal field splitting energy and the energy is related to wavelength in an inverse relation, the energy is related to wavelength in an inverse relation, right? Clear? So in between 1 and 3, which will have high energy? High energy will be with the one which have high number of ethylene diamine, as it is a strong filled ligand. So high energy for 3, low energy for 1. Wavelength is inversely related. That means high wavelength for 1, low wavelength for 3. High wavelength for 1 and low wavelength for 3. Till here, if you understood, right? Okay, till here you understood, right? It's very easy. We just solved one part here, that yes, we are replacing water with ethylene diamine. We know ethylene diamine is a ethylene diamine is a strong filled ligand. So if you are replacing with a strong filled ligand, the crystal field splitting energy is high, right? The energy is high. For 3, the energy is more than 1. Okay. The energy and wavelength are inversely related. So that means the wavelength for 1 will be higher than the wavelength for 3. On the basis of that observation only, we eliminated these two options, because for these, the wavelength of first is lower than the wavelength for third. Wavelength of first is lower than the wavelength for third. Okay. The question asked for the wavelength only. Okay, so that means B and C are incorrect. If B and C are incorrect, the correct option will lie in between A and D. Right? Now, if you know that 310 nanometer falls in the UV range, it falls in the UV range, and ultraviolet range is not visible at all. You can't see it with your eyes. Okay? You can't see it with your eyes. But we are able to see these colors: pale blue, blue, violet. These colors are shown by, now you can observe these colors only while they are written here, right? So that means this option does not relate with these. There is a discrepancy in the data, right? Because it comes in the UV, right? That is not visible. These all are visible. These all compounds are visible. Okay. So that means this is the incorrect option. Your correct option is option D. Now supposedly by some mistake, this value was also around 500 something. Then how would you have done it? Supposedly, there is one more approach. Okay, yes. So there is one more approach I told you. We have this complementary color wheel. The color that you are seeing here is a complementary color of the light that is absorbed. Suppose this compound, it absorbed orange color, and it gave what color? The complementary color is blue. If it absorbed orange color, it gave blue color. If it absorbed yellow color, it will give the complementary violet color. Clear? This is the complementary color wheel. Why I needed you to know? Because I needed this orange and yellow to fit in the data. How? Now see. This is VIBGYOR. From when you are going from violet to red, the wavelength is increasing. 400 nanometer to 700 nanometer. YO, yellow, orange. Yellow has a lesser wavelength than orange. What is the range? Orange is close to red. Red is 700, so orange will be around 600. Okay, and for yellow, it's lesser than orange, which is less than 600. Let's say it's 500, 550 something. So for yellow, it's 550. Now see your options. The option D matches perfectly with the data, or for first compound, the wavelength is 600 nanometer. The wavelength of the light absorbed is orange. Orange wavelength is 600 nanometer, and for yellow is 535 nanometer. I did all that. Why? Because sometimes even in exam, due to pressure, you forget the correct values of wavelengths. They are a little difficult, but remember this 400 to 700 range. Okay, and anything below that comes in UV range. Okay. The color knowledge is needed for this type of questions, yes, because it's a color based question. This is the color wheel you need. VBGYOR. Make 6 sections, right? VBGYOR. The color that are in opposite to each other, they are the complementary colors. So if violet light is absorbed, the color shown will be yellow. If blue light is absorbed, the color shown is orange. If red light is absorbed, the color shown will be green. It's like that. Complementary color wheels. normally people design their outfits like that only. The clothes that normally they wear, they design it such way they're complementing each other. So the combination will look nice. That's the color wheel, color theory, right? Yes, it's this is the color knowledge. That's all you need. That's all you need. That's the only color knowledge you need. Okay. Let's move on to the next question. For the crystal field splitting in the octahedral complexes. For the crystal field splitting in the octahedral complexes. You guys are not liking this session. You guys are not liking this session at all. You came to see me, yes, to study also. Do like the session if you are understanding it. I know these questions will seem a little tougher, but if you practice them, trust me, it's going to get easy. Okay, I have practiced them because I've been solving them for so long. That's why I know what formula to use. For you also, it will come with practice. Not from the day when you won't get it. It will take time, but you need to put the effort. Okay, for now, do like this session. Okay, if you are understanding it and if it's making any concept easier for you. Okay, so when we are talking about splitting in octahedral complexes, the splitting goes like this. Let me change the color. See, this is the at ground state. Okay, this is d orbital at ground state. Okay. It splits, it increases in energy. I don't have the space here. I'll do this only. Okay, this is the d orbital. It is raised to excited state. Okay. Something like this. Okay. Then it splits. In case of octahedral, it splits as T2G and Eg. T2G and Eg. T2G is dx square minus y square and dz square. Sorry, Eg is dx square minus y square and dz square. T2G is dxy, dyz and dzx. Okay, this is ferric center. So the Eg orbitals are raised to, say UV rays because your teaching made us to see. No, you can't. You still can't see UV rays. You can't see it. B. Okay. So the Eg orbital are raised to a power of this much. How much power is this? Plus 3/5 del O. Okay. And T2G are decreased in a power, how much? Minus 2/5 del O. Minus 2/5 del O. So which option matches it? Eg orbital will decrease. No, it won't decrease. For Eg orbital, the energy is increased. See, this is the excited state energy. They are going higher than that energy. So it is increased by how much? Plus 3/5 del O. So it is increased by 3/5 del O and it will decrease. For T2G, it decreases by 2/5 del O. Del O is your crystal field splitting energy for octahedral complexes. O means octahedral complexes. Okay. Energy will increase and that of T2G will increase. No, it's not increasing. For T2G, this is the excited state energy. For T2G, it decreased. For Eg, it increased. Increased by how much? Plus 3/5 del O. And for T2G, decreased by how much? Minus 2/5 del O. Okay. This is the excited state energy. Excited state energy. This is ground state. From ground state, it went to excited state. From excited state, splitting happened. Eg and T2G. Eg got higher by 3/5 del O. 3/5 del O and T2G got lower by minus 2/5 del O. Okay, so that means your correct answer is option B. How many of you answered option B? Let me see. Yes, so 78% answered option B. Correct. Next question. What kind of isomerism is this? What kind of isomerism is this? Is this geometrical? No, it's not. Why? There is no cis-trans isomerism existing between them. Then you have optical, again non-superimposable. Nope. Hydrate, is there water molecule involved here? No. So the correct answer is, okay, the correct answer is linkage. Now this type of isomerism is shown by ambidentate ligands. It is shown by ambidentate ligands. What are ambidentate ligands? Those are those ligands which have two donor sites, but they only bond by one donor site at a time. At a time they only bond by one donor site. Okay, so if say I have two hands, right, but I am not ambidextrous. I'm not, some people are ambidextrous, right? They uses both hands. For me, if I'm using my one hand, my other hand won't be working, right? I can okay, it's like ambidentate ligands. They have two donor atoms, but either of them will be involved in bonding at one time. Okay, both won't be involved, only either one of them will be involved. That is ambidentate ligand. For example, NO2 is an ambidentate ligand. Okay, it can either bond from nitrogen side or it can either bond from oxygen side. But if it is bonding from oxygen side, the nitrogen side will be sitting there. It won't be bonding with anything. Okay. Similarly, if it is bonding from nitrogen side, the oxygen side will be sitting silently. It won't be bonding with anything. Okay, it won't be bonding. Okay, yeah, what you want to ask? You don't came to study, you came to see me, so study also, no? Okay, so what type of isomerism? Linkage isomerism, shown by ambidentate ligands, when ligands differ in their connectivity to the central atom. When ligands differ in the connectivity, in their connectivity to the central atom, that is linkage isomerism. Okay, these kind of compounds, this is an example of linkage isomerism. This is an example of linkage isomerism. Yes, ambidentate shows linkage isomerism. That is correct. Ambidentate will always show linkage isomerism. Okay. A. Yes, the correct answer is option A. Let's move on to the next question. Geometrical isomerism is exhibited by square, planar, tetrahedral, octahedral. See, geometrical isomerism comes to cis isomerism, cis trans. Geometrical is cis trans isomerism. Right, there is difference in position. What you call cis? So when you have same ligands on the same side, adjacent side, when you have the same ligands on adjacent side, that is cis isomerism. Okay, and when these same ligands are present on the opposite side, that is your trans isomerism. Clear? Now one thing is there, square planar. I don't know if you can imagine it or not. I will use a book. Yeah, I'll use a book. Okay, so if you have like this is an example of square planar. Square planar means your metal is in between this. Here it is the metal, your metal or atom, central metal atom. Okay, on the corner of these books there will be ligands 1, 2, 3, 4. Okay. 3, 4. This is a square planar arrangement. Okay, in this case you have different position. So for example, if two ligands are here, one here and one here, this will be a cis arrangement. But if one ligand is here and one ligand is here, same ligands are on the opposite side, that will be a trans arrangement. Octahedral also same thing. Octahedral is similar to square planar, but you have, if let's say if I stab this paper and I go both side like this, in between, like, you know, if it stabs here, one above and one below, square planar and then one above and one below, that is your octahedral arrangement. In octahedral arrangement, there is distinction between all these positions. So yes, in that case also cis and trans is possible. Right? If you have, let's say, one ligand here and one ligand here, so that is a trans position. They are in opposite to each other, right? Cis means they will be on the same side. But for tetrahedral, the case is a little different. Okay, so I'll show you. You should know the concept, because if you are just blindly memorizing it, it won't help you much. Okay, so for tetrahedral, the arrangement is similarly slightly like this. Okay. The angles are 109.5 degrees. the angles are 109.5 degree. The arrangement is like this. Okay, this one is straight actually. 109.5 degrees. Okay. Okay. Now, if I'm putting one ligand here, A here, and A ligand here also. Okay. If I'm putting one ligand A here and the other ligand A here, they are what? Cis to each other, right? They are what? Cis to each other. Okay. Similarly, if I'm putting one ligand here and okay, I did this and then I shifted it a little bit. Okay. If I'm putting one ligand here and one ligand here, they will be cis. Similarly, if I rotate it like this, the blue one will come up, right? If I rotate it like this, these two positions will be cis, these two positions will also be cis. All the positions are totally equivalent in case of a tetrahedral complex. As you see, because you can't differentiate, all the positions are cis. There is no trans isomers, right? Geometrical means there is one cis and one trans. Here only cis is happening. Only cis is happening. All the positions are equivalent to each other. If you rotate the whole molecule, even all the positions are still equivalent. In that case also only cis isomers is possible, right? No trans isomer is possible. That's why tetrahedral complexes cannot show geometrical isomerism. Tetrahedral complexes cannot show geometrical isomerism, right? So the answer is square, planar and octahedral complexes. Okay, so that's a simple one, right? Because all the positions are equivalent, all are cis. There is no trans possible for a tetrahedral complex. A, C. Why are you answering C? The C is not the correct answer. B. As I told you, tetrahedral complexes do not show geometrical isomerism because all the positions are equivalent. We just saw that, right? Because every position is cis to the other position. Every position is cis to the other position. No trans possibility is there. There is no possibility for trans isomers, okay? And if trans is not there, only cis is there, that is not geometrical isomers. Geometrical isomerism exists because there is a difference in position, right? Cis and trans, difference in position of ligands. Okay, so the answer is B, not C. Tetrahedral do not show geometrical isomerism. Next question, the effective atomic number of chromium is in this complex. So the effective atomic number formula is really simple actually. Effective atomic number is Z minus X plus Y. Z minus X plus Y. Z minus X plus Y. Here Z is the atomic number. Z is the atomic number of that metal, of that atom. Okay. X is the oxidation state and Y is the number of electrons donated by ligands. Donated by ligands. So we'll calculate here. Tell me the answer for this one. It's very easy. Okay. So for chromium, Z is what? Chromium. Z is 24. Z is 24 minus oxidation state. In this case, what is the oxidation state? Simple. NH3 is neutral, no charge. Chlorine has charge, minus 3. 3 chlorine are there, minus 3. To balance this minus 3, this compound, this complex will have plus 3. So that means the oxidation state of chromium is plus 3. Okay. Plus 3. Okay. Plus. How many electrons are donated? Ammonia is donating 6 electrons. Ammonia is donating 6 electrons. So the answer is 27. So the answer is 27. How many of you answered B? Okay, almost. It's never 100%. You're not sure, eh? Sometimes you do 35 also. Wow. Okay, B, done. Okay, done. The answer is 27. Simple formula, atomic number minus the oxidation state plus the number of electrons donated by the ligand. Okay. Let's move on to the next question. The hybridization state of cobalt in K3 high spin. See, it's already written. It is high spin. High spin means that there will be no pairing. High spin means no pairing, right? Low spin complexes are the one where electron gets paired, but in this case there will be no pairing. It's already written, it's a high spin complex. Okay, what is the electronic configuration of cobalt? It is argon, iron cobalt, 3d7 4s2. Okay, what is the oxidation state of cobalt here? Cobalt's oxidation state is +3 here, right? If I take this x, -6 equals to -6 equals to -3. So x will be equals to +3. So if I remove 3 electrons, cobalt 3 positive, it will be argon 3d6. Argon 3d6. Clear? That is the electronic configuration of cobalt 3 positive. We need to fill the electrons. Okay, let's see. 3, 4, 5. This is 3d. Then we have 4s. Then we have 4p. We are figuring out the hybridization here. Okay, and we have 4d. Clear? This is the configuration. Now 3D is full till 6. 1, 2, 3, 4, 5, 6. Okay. Now I'll use a different pen. Okay. You have how many electrons to fill? You have 6 fluorine electrons. You have 6 electrons that are coming from fluorine that you need to fill. Do you have any empty orbitals? The pairing can't happen. You don't have any empty orbitals. You need empty orbitals so that you can fill these 6 electrons. These 6 electrons. Okay. Wherever you fill these 6 electrons, that will be the hybridization. That will be the hybridization. Carbon hybridization state. Okay, I'll explain. After this, I'll explain. Okay. So, how will you fill these 6 electrons? I see 6 orbitals. 1, 2, 3, 4, 5, 6. I see 6 orbitals, right? And it's already saying that it's a high spin. That means high spin. There is no pairing involved here. High spin complex. Okay. So, I'll fill 1, 2, 3, 4, 5, 6. These are 6 fluorine atoms. Okay, these are the 6 electrons given by fluorine. Okay, these are the 6 electrons given by 6 fluorine atoms. Okay. A, some of you answering A, B, D. Wow. A, B, D. B is not there, D is also not there. So what is the hybridization? S, P3 and D2. S, P3 and D2. That is the hybridization. S, P3 and D2. A, right? A. Yes, A. Now a little bit SP, SP2, SP3. So hybridization, it's a PU1 concept. Okay, I know you might get confused. In chemical bonding we have studied hybridization. So we have 3: SP, SP2, SP3. Carbon majorly shows these 3 hybridization: SP, SP2, SP3. Now that depends on I'll give you one simple formula for calculating hybridization. It will work on any compound if you are calculating in. Okay, here it's different, but for those compounds it will work. In coordination, you have a different approach to hybridization. For other compounds, it's simple. Half hybridization will be equal to half of number of valence electrons. Okay, just write down with me. V is the number of valence electrons. It can't be D2sp3, Darshank, because for D2sp3 you need to vacate these 2 orbitals. You need to vacate, you need to do pairing. This should go here and this should go here. There should be pairing. But since fluorine is a weak filled ligand, it can't do pairing. Since fluorine is a weak filled ligand, it can't do pairing. Second thing, it is written here, it is a high spin complex. High spin means there is no pairing involved. High spin means there is no pairing involved. Okay, read the question, it's in the question only. And if you somehow misinterpret it, fluorine is there. Fluorine is a weak filled ligand, it won't do pairing. That's why these 2 orbitals can't be used. Okay, if these orbitals were used, then it would be D2sp3. If these orbitals were used, okay, but we are not using these. We are starting from, we are filling from here, sp3d2, outer orbital complex. This is an outer orbital complex. Okay. Now see, there's a difference between sp3d2 and d2sp3. d2sp3 is normally formed by strong filled ligands because they can do pairing. They form d2sp3 complex. I know both form octahedral only, but the hybridization tells us about the strength of the ligand also. d2sp3 strong filled ligand, sp3d2 weak filled ligand, outer orbital complex. Okay. Okay. Let's figure this out. Hybridization is half of number of valence electrons of that atom in neutral state. Normally how many valence electron they have, plus number of monovalent atom minus cation plus anion. Okay, that is how you calculate hybridization. Okay, now this concept I'll explain. sp hybridization, sp2, sp3, they varies on the percentage of s character, how much s character is there. For sp, the s character is 50%. Here it is around 1 by 3, 33%, and here it is 25%, 25%. Okay, that's around that. Okay, when carbon is bonded to, when carbon is in triple bond, carbon-carbon triple bond is there, the hybridization is sp. When carbon-carbon double bond is there, the hybridization will be sp2, and when carbon-carbon single bond is there, the hybridization will be sp3. That you determine on the basis of this hybridization. Basically you will get a number here, I call that steric number. You'll get a steric number here. Depending on the steric number, you will have the hybridization. If the steric number is 2, the hybridization will be sp, 1s, 1p. If the steric number is 3, hybridization will be sp2, 2, 3, hybridization will be sp2, 1s and 2p, 3 ho gaya, right? sp3, the hybridization will be, the steric number will be 4, which means 1s and 3p, that is 4. Okay. K3's role is to stabilize it, to make it neutral. If K3 was not here, it would be COF6 3 negative. Yes, it would be COF6 3 negative. It's not to interfere anything, you just calculate the hybridization using that. Okay, sigma and pi bond topic, we'll come to that in chemical bonding and molecular structures. For now, just a basic idea, steric number, how steric number is related to hybridization. Okay, there's one more formula, but I'm not giving you that because you'll get confused more if you don't know the topic. Thirteenth question, the electron ligand donates 6 pair of electrons, which is equal to 12 electrons. So 33. Six. Hold on a second. It donates only yeah, it does though, but 30, yeah, 6. NH3 will donate, yes, it will donate 2 electrons. Yep. 12, yeah. Yeah, correct, I forgot it. I didn't count the 2 other electrons. Yeah, Gayatri, correct, Gayatri. Yes, I did the mistake here. Sorry. Okay, so NH3 normally it already have bonded with hydrogens, right? So it has only these 2 electrons that it will donate, right? So from one ammonia we are getting 2 electrons, and there are 6 ammonias there. Okay, so that will be 12 electrons. So here the Y will be 12. Okay, and if it is 12, the answer will be 33. I did mistake. I was thinking, but I don't know. Sorry. Okay, yeah. So when bonding is happening, nitrogen is donating ammonia is donating 2 electrons, right? So 2 electrons and 6 ammonia are there, so it will be 12 electrons. Why is 12? The answer will be 33. Thank you, Gayatri. Okay, and sorry for the yes. Let's solve the next question first. Okay. Hybridization state is done. The spin magnetic moment of cobalt in this complex. We have this complex. We need to find the spin magnetic moment. I'll give you the formula first. The spin magnetic moment is N into N plus 2 Bohr magnetron. And N is the number of unpaired electrons. N is the number of unpaired electrons. So you calculate the number of unpaired electrons first, which is for this complex, for cobalt, how many number of unpaired electrons are there? Okay, so let's see. Okay. Firstly, it is tetrahedral, right? So it will split like this. I'm just drawing the splitting. Clear? Okay. Cobalt again 3d7 4s2. What is the oxidation state here? X minus 4 equals to minus 2. That means X equals to plus 2. 3d7. 7 electrons we need to fill here. 7 electrons we need to fill here. 1, 2, 3, 4, 5, 6, 7. Clear? For tetrahedral complexes, one thing you need to remember that this energy gap for tetrahedral complexes, this energy gap is really less. So instead of pairing, it will rather jump. Okay. So if I say jumping from here to there needs very less energy, then I need to go outside and find some person to pair with me. Okay. That is much more energy consuming. The thing that is less energy consuming, that thing happens. Okay, some little concept. If your crystal field splitting energy is less than the pairing energy, delta P is pairing energy. If it is less than the pairing energy, what will happen? It will move, right? It will jump to the next orbital. But if your pairing energy is less, then this crystal field splitting, this splitting energy, it is lesser, the pairing energy, then pairing will happen. Okay, then your pairing will happen. Whichever energy is less, that process will happen. Okay, if splitting energy is less, electron will jump to the higher orbital. Okay, and if your pairing energy is less, electron will get paired. For tetrahedral, this energy is much less. So even for so for tetrahedral, this energy is really less. So electrons rather jump than getting paired. Okay. What should be the answer for question number 15? Okay, so for this one, how many unpaired electrons are there? 3. How many unpaired electrons are there? 3, right? So N is equals to 3. N is equals to 3, and then magnetic moment will be equal to 3 times 3 plus 2, which is square root of 15. Yes, 5, 3, 15. Yes, so the correct answer is option C. Now let's see how many of you answered option C. Yo, why are those votes so close? I am going to lose in KBC if I went with you guys. Hg oxidation state is plus 2. Mercury makes plus 2. Hg oxidation state is plus 2. How many questions? Any other way to find out? Easy way. What easy way? Hey, what are you talking about? Any other way to find out what? Oxidation state? Okay, yes, so why D? Sunita, why D? The answer is not D. Oh, SCN is actually a weak filled ligand. Okay, you remember that series you have, right? That series from halides, then you have oxygen compound, then you have nitrogen compound, then you have pi acceptors, right? That whole series you have, you remember that. That is the sequence from weak filled to strong filled ligands. That once you remember it, for coordination compound you need to remember it. Tricks for finding that. Finding what? That weak filled, strong filled ligand. Easy way. So the easy way will be through practice. Actually, you see from in the last year questions, previous year questions, what kind of actually ligands are being asked. Normally they ask, for example, I remember it like this. I have a general idea, so I have this. If this helps, use it. Halides, weak filled. They are the weakest filled ligand. Then after halides, I have oxygen compounds. You have water, hydroxides and all. Then after that you have nitrogen compounds, and then after that you have pi acceptors. Okay, this is to give a rough idea. I just remember it to give me a rough idea. And also I remember some of the ligands that are more commonly used. SCN is a weak filled ligand. It comes comes near here only. Okay, it's a weak filled ligand. Halides, fluorine is a weak filled ligand. COCN, these are strong filled ligand. I already remember that. COCN, strong filled ligand. H2O, weak filled ligand. Ammonia, weak filled ligand. Okay, mostly weak filled. Strong filled may you have really less examples. Okay, so with practice you will get to know that. Okay, but that table, that not table exactly, that sequence is very important. Do memorize that sequence once. It's very easy once you memorize it. Okay. Okay. Vineet, cutoff for RVCE. Ma'am has covered that video. You can check it, the previous year cutoffs. Jasmine ma'am has covered a video about that. You can go check it out for RVCE, what was the last year cutoffs and before that also. Okay. I told you this sequence: halides, oxygen compound, nitrogen compound, pi acceptors. Now just fill in the data. Halides may you're starting from which halide you are starting from: I negative, Br negative, F negative, Cl negative. Okay, and then you are going to oxygen compounds, nitrogen compounds, pi acceptors. Just fill in few halides. Write down here the halide sequence, oxygen compound sequence, nitrogen compound sequence, pi acceptor sequence. Okay, don't have the time to learn the mnemonics now. Spectrochemical series, sorry. I have questions left. Spectrochemical series. That series is spectrochemical series. Okay, thank you. You want me to talk in Hindi? What do you want me to talk in Hindi, macha? Which of the following system in an octahedral complex has maximum unpaired electrons? Very easy. Maximum number of unpaired electrons. Maximum number of unpaired electrons. Number of electrons can be done by formula atomic number minus oxidation rate. EAN number you are talking about, Saif. Okay, so for D9 high spin, I can just solve here. I don't have to write anything. D9 high spin. D9 will obviously have the least, even if it's high spin, even if it's low spin, only one electron will be unpaired. 9 will be paired, no. Okay, D6 low spin. D6 low spin. Low spin means pairing is there, right? Low spin means pairing in there. This is for octahedral complexes. So pairing will be there. 1, 2, 3, 4, 5, 6. There will be pairing. So obviously no unpaired electrons. How many? It has 1 unpaired electron. It has 0 unpaired electron. D4 low spin. D4 low spin. 1, 2, 3, 4. Low spin means there is pairing. High spin means it has a shift. It has crossed the this barrier and went to Eg. High spin means it, instead of pairing, it went to the higher orbital, Eg orbital. Okay. How many electrons are there? 2. Now you have D7 high spin. If I am talking about D7 high spin, I'll make here. Okay, D7 high spin, that means pairing won't happen. Firstly, the electron will get filled to the higher one. 3, 4, 5, 6, 7. How many unpaired electrons you see? 1, 2, 3. 3. The maximum number of unpaired electrons are present in D7 high spin. This high spin and low spin, you should be aware. What are we talking about here? Low spin means pairing is involved, pairing is happening. High spin means that pairing energy, no pairing is happening. What is happening? The electrons are getting shifted to the higher orbital. The electrons are getting shifted to the higher Eg orbital. In octahedral complexes, Eg orbital. Clear? So each one of you vote what is the answer. You guys are not liking the session. You are not liking the session at all. Okay, I won't be teaching in the next class. I'll find some other. We'll send Aishwarya ma'am only. I won't be taking your doubt classes. Yes, you don't like the session. For magnetic moment, what your sir told? Electrons can be done by formula atomic number minus oxidation state. For magnetic moment, the formula is simple, root square root of n into n plus 2. And is there any short trick for that? I don't know. You just know it when you're filling the electrons, how many electrons are there. Maybe if that's the short trick your college professor told you, you use that. Okay, I don't have no idea about that short trick. Okay, from the next class, Aishwarya ma'am is coming, as you guys are not liking my sessions at all. So I'll ask, and the Aishwarya ma'am will take your class. Okay, done. Your promise. Okay, now let's see if we have any other question. Yes, we do have one more question to go. So the crystal field splitting energy for this complex. Now you can see this is an octahedral complex. This is an octahedral complex. This is 18,000 centimeter inverse. The crystal field splitting energy for this one. This is a tetrahedral complex. Okay, now you should know the relation between these two. The crystal field splitting energy of octahedral complexes and crystal field splitting energy of tetrahedral complexes. You should know the relation between these two. Okay, what is the relation? What is the relation? See, if you guys didn't like it, if you guys didn't do at least 50 likes to my session, I'm not taking the next class. I'll ask Aishwarya ma'am, she'll come and take your lives. Okay? Because you have been like, we've been here for more than 3 hours and you guys are not even done 50 likes also, yeah. Repeat classes. Number of electrons in magnetic moment. Okay, Seth, if it's a short trick your professor gave you, so use that trick, okay? If it's saving you some time, use all those formulas, okay? You need that. Is it A or B for previous one? So for previous one, the answer was D actually. The answer was D. Sorry, I didn't mark it. The answer was D, the maximum number of unpaired electrons. Okay? How to find geometry? You learn geometry actually. That will come in chemical bonding. How to determine the geometry, you use that. With different type of hybridization, different type of geometries is associated. Then after geometry, one more thing comes. Shape. That will be different depending on the lone pair, bond pair interactions. Okay? Yeah, we'll discuss all that detail in chemical bonding and molecular structures. There are questions on geometry, there are questions on bond order, molecular orbitals, all questions regarding that, okay? We'll discuss it. And yes, I am really serious about it. If you guys didn't do at least 50 likes, I am not taking the next class, okay? Let's see the next question. Might be our last question. Crystal field splitting energy for octahedral complex. This is octahedral complex. It is 18,000. For this complex, you need to find. This is a tetrahedral complex, right? This is the crystal field splitting energy for tetrahedral complex. Okay. Now, what is the relation between them? Between tetrahedral and the octahedral splitting energy. The crystal field splitting for tetrahedral complexes is related to crystal field splitting for octahedral complexes. In what way? The formula is simple. It is 4 by 9. 4 by 9 of the tetrahedral energy is 4 by 9 of the octahedral one. Simple, right? Straight away formula. And you only have two shapes here, octahedral and tetrahedral. You only have two shapes here, octahedral and tetrahedral. A. How many questions this chapter weight is? So, Bhagya, the questions will be coming anywhere between the range of 3 to 5, okay? 3 to 5. It will come from this chapter. It's a very high weightage chapter, one of the high weightage chapter, okay? So, 3 to 5 questions you'll see there in your exam, okay? Solutions I have done. The first lecture was of solution and electrochemistry. As we know, we have like little bit leniencies going on, I know, because we have just started it, as in you have some time, and when you have time, you people procrastinate, you don't study, right? But I thought start from the high weightage chapter so that by the end you will have time to revise it, because we'll do revisions also. Okay. Went very bad. Will exam 2 be more difficult and unpredictable and high level? Exam Ayo, Microsoft, the exam was really easy. Not easy, but it was moderate level. I checked the questions. I also, yeah, the questions were not, MCQs were very easy. Why? What are you saying? Came in JE from this topic. Yeah. JE is different. JE, maybe you'll see the questions from this chapter, but KCET also 3 to 5 questions will come from this chapter. So tell me, this is simple. You guys would have solved it, right? What is the answer? Simple. The value is given for the crystal field splitting for octahedral complexes. It's 18,000 centimeter inverse. 4 by 9 times 18,000. That is the crystal field splitting for tetrahedral complexes. That is this crystal field splitting for tetrahedral complexes. 8,000 centimeter inverse. How many of you answered A? A, yes. Manaswini answered A. 11th classes chapter for KCET. Saif, you can skip if you don't want those 20 marks. So because PU1 weightage is around 17 to 20 marks. So if you are willing to take that risk, if you said that I'll score more in other physics and biology or maths, so you go with that strategy, but PU1 have some weightage. More importantly, the weightage is in your knowledge level, because if you have studied PU1 correctly, you will have the good basic for understanding all this. Okay, PU2 you won't understand PU2 if you have not studied PU1 properly. Okay, there will be some knowledge gap. Don't skip it, I would say. Okay, so if you have time, do that, but yeah, prioritize PU2 more than your PU1. Okay. Ma'am, now you can't leave, we have to take class, because likes are 51. They're not. I am still seeing 48 only. In my feed, it's coming 48 only. Yeah, so I think this is our last class. Sad guys. It's okay, it was nice knowing you all. Yeah, I remembered your name also. So the answer for this is, okay. Don't skip it. I would say don't skip it. From there, 3 hydrocarbons, equilibrium, redox. If you have time, focus on these 3. These comes in the medium weightage category. Hydrocarbons, redox reactions, and equilibrium. Okay, I think we're done. Focus on these from your PU1. Don't skip completely. Practice some questions so that you are not losing those 20 marks completely. Okay, I know you guys can. GOC, yeah, GOC. GOC, the methods are little important. You have the effects, electronic effects, inductive effect, and then you have the hyperconjugation, resonance effect. These effects are very important. And also the Dumas method, Zeldal method. The mainly focus on nitrogen, carbon, hydrogen detection. Nitrogen, carbon, hydrogen, these 3 methods. And in nitrogen also Zeldal method. Okay. And yeah, focus on these questions, the electronic effects and these detection of these elements. The formula, straight away questions will come if come. 1 question will come, 2 question will come, not more than that. Okay. Ma'am, say some short tricks for GOC. Tricks for GOC. Okay. So firstly, you should understand what those effects are. If you understand the concept, then the tricks will work, right? If you don't understand anything and you're just going by tricks doesn't work 100%. They work 70-80%. Okay. 20% you need the concept. So if you have the concept, what about remaining chapters? So remaining chapters also have weightage, as I've told you. These comes in like 2-3 questions you can see, 2 questions, 3 questions you can see. Okay, and the rest topics, rest chapters, 1 question, either none question or 1-2 questions will come. Okay, so it's like that. Question wise weightage I'm telling you. Okay, remaining chapters. Okay, Yeah, the likes are still less. So sad I have to leave. It's okay though. Okay, it's okay. For this question, the answer is option A. And how many of you answered that? 65% of you. Okay. Ma'am, questions same ask in KCT or applied? Ask in KCT or applied. So, same question as in thermodynamics has not much weightage. It's a very lengthy topic, I know. But 1-2 questions max. 1 question, 2 question max. It's not that of importance. Okay, I know it's very hard. It's very difficult for you guys. From 11th, when will you take? 11th? Next week. Next week we are doing 11th only. I think so. Yeah, next week. Okay, in GOC, but the estimation method is difficult. The estimation methods are difficult. That's why I am telling you. Just remember the formulas. We have, how many we have? We have oxygen, phosphorus, sulfur, and halides also, halogens also, right? Yeah, for these and these, you just need the formulas. So focus on nitrogen, carbon, and hydrogen. Questions I have seen, they come from this nitrogen mostly, then carbon and hydrogen questions. Okay, and rest were okayish. So I know estimation methods are little difficult, but if you focus on these formulas of these estimation methods, what will be the percentage of nitrogen, percentage of carbon, percentage of hydrogen, that is more important. Okay, straight question will come. From PU1, are you asking from PU1? So theory questions, it will be like a mixed match. No, not all questions will be calculative in nature, not all questions will be theoretical in nature. There will be a mixed match of that. You will save some time on some questions, you will take more time on some questions. It will be like that. Okay. KCT or any college exams and syllabus for entrance exams. GUG, KCET, I don't know. The syllabus will be different, but all have a common thing, that is NCERT. They take their inspiration from NCERT. The whole syllabus is designed using NCERT only. Okay, so I don't have idea of GUG, Gujarat CET, I think, but KCET I have an idea. So that's why I'm teaching here. I'm sorry, Dushala. Okay. Comet K will help. Don't worry. We are planning for Comet K. Don't worry. Okay, we'll help you with Comet K. What are the chances of appearing more question like theory based more than numerical? Yeah. I answered already. Yeah. Comet K will be there. Don't worry. Okay. For now, focus on KCET questions. If you are preparing for Comet K also, these questions will serve you as a baseline actually, because Comet K question levels are little higher than this one. Okay, but if you practice them first, you will have an idea what you are doing for the rest of the questions, which are little high level. I'm not ignoring you, Meera, I know. Okay, yeah, okay, so you guys did it. Okay, I am just, yeah, again I told you, Bharat, from first PUC question, marks I can tell you the exact will be 1-2 questions from each chapter, something, no questions. You are registered for Comet K. That's very nice, Naveen. Live class timings from 9 AM, one live, and the second live will be at 5 PM. Okay. Yeah, the likes are increasing, I think. Okay, Comet K is hard than KCET. See, nothing is hard. It's in your brain. Okay. The syllabus is totally same. The question level is a little different, not difficult, little different. Okay, if you take it difficult already, you won't be able to solve it. Okay, in your mind already you have made your mind that this is difficult. I may not be able to solve it. Trust me, you can solve it. It will take some time. You will need to sit down for longer duration. You need to solve more questions. You need to understand the concepts. You have time. You have time for that. It's in May, right? April. Yeah, it's in May. Yes, Naveen, I am from Tamil Nadu. This whole crash course for Comet K as well as for KCET, all are in complete English, pure English. NEET, we don't have anything right now, Macha. It's okay. We'll see if something can be done. Okay. From second PUC, whole paper will come from second PUC. 40 marks, 45 marks weightages from your PUC, second PUC. Class is done actually. I think this is the last question, or do we have? The class is done actually. Yes. I'm just chatting with you guys for a bit. I'm going to leave it now. Okay. Previous message. Yeah. So, Naveen, right? Don't worry. The crash course is completely in English. Okay. For NEET, we don't have anything. Thank you, Naveen. Okay. Okay, so only consider engineers in case. Yes, if you are applying for engineering colleges, if your dream is to go to an engineering college, then you need PCM. Maths is required. Tomorrow physics, you will get the notification on the WhatsApp channel. Yeah, the WhatsApp channel, you'll see all the details there. Okay. Vinita, I have no idea about that. I will get back to you in the next class. Don't worry. Okay. Yeah, the current class is complete. Okay, I am going to leave you guys. Bye. If you have, I was waiting if you had any doubts. Yeah, I saw the likes meet. Thank you. Thank you all, and yes, take care. Bye bye. See you in the next one. Okay. Yes. Okay. Take care. Bye.